Sí, bueno, sí. Sí, dos, tres, sí. Probando audio, sí. Sí, como no, sí, dos, tres, sí.
Bueno, bueno, 1, 2, 3. Probando, probando.
Sí, de hecho ya lo estoy poniendo.
Prueba de sonido. 1, 2, 3.
Good morning. I just wanted to ask the people that has not yet sent the poster, please do it right now. Otherwise, it won't be included in the USB on the memories. I only have like 9, and there was supposed to be 20. So please send me your posters. Thank you.
Good morning, everyone. Welcome to Season 7. My name is Freddy Pranajaya from University of Toronto in Canada, and next to me is Mr. Narayan Prasad from Space Program Limited in India. Before we begin, I have 2 announcements from Werner, and the first announcement is that please fill in your feedback form. That is part of your package that you receive when you come in, and please return it afterwards. And the second thing is in the afternoon, there will be a discussion session to get your input and then discuss about what you have observed, and perhaps you have any additional suggestion for the future workshops. And if you do want to have suggestion, please provide it to Werner, and his email is it's Werner Balog. Sorry. Yes. So WERNER.BALOGH@UNOOSA.org. And please include your observation and recommendation, of course, in the email, so Werner can make sure to take them into account for the future workshop. Okay. Our first speaker is Mr. Fernando Aguado Aguilet.
Yes, perfect. So it's quite difficult to pronounce my second family name, but I pronounce like a native. Thank you very much, Freddy. For me, it's an honor to be here. So I think that this is my 6th time that I assist BSTI Simposio. So I am very, 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 very happy to have the opportunity to be here. Today I'm going to present the Brazilian contribution to the HumeSat constellation. So the HumeSat project, I will give some basic ideas. We have been the creators of the HumeSat system. It's an international initiative for building a constellation of nano satellites providing communication capabilities to areas without infrastructure. So the idea is to connect a set of users with a network of worldwide distributed sensors, and can be used for different applications. What we are going to provide and we are providing is not an application, it's a service. So you can choose the application for what you want to use this service. So, for example, we can, monitor essential climate variables, and also if we have some emergency situation, we can send hazard messages. Currently, we are working in HumeSat 2.0, including new aspect that we have, learned from our first demonstrator that we have already sent 1 year ago, in order to improve the performance of the system. And I'm going to present some guidelines right now. HumeSat constellation is recognized through the most important institution, agencies. For me, it was absolutely an honor. It was my dream that this office, the Outer Space Affairs Office of the United Nations, in a Congress in Vienna, approved to include the HumeSat constellation as a BSTI project. So, additionally, we have been supported by different agencies, and in our case, ESA have supported us a lot. And currently, we are working, and we are going to launch in cooperation with the agency, a consortium of Brazilian agencies, universities, is going to launch the second HumeSat satellite, and we are cooperating with them. So the institutions, ESA, Mexican Space Agency, Brazilian Space Agency, the Spanish government, our local government, a lot of universities, because the HumeSat concept was initially, promoted by the University of Mexico, UNAM, Cal Poly, also with cooperation with La Sapiencia. Also, we are now cooperating with a lot of Brazilian universities and our university in Spain. So it was based in a cooperation scheme, absolutely.
United Nations Conference on Sustainable Development held in 2009 selected within the Basic Initiatives Program of the United Nations the HumeSat project submitted by the University of Vigo. This program meant a substantial change in the United Nations sponsored project due to the fact that it was included for the first time the development of satellites and not just applications in the space field within the programs of international cooperation. HumeSat satellites, born with a strong nature of international cooperation with emerging countries, will receive and store information, and through the ground stations of the worldwide NASA network, they will provide the data transmitted by bidirectional low-cost sensors to the final user. This data will help to study climate change in areas without telecommunications infrastructures. Also, they will transmit information in emergency situations where the infrastructures were significantly damaged caused by natural disasters or wars. The first demonstrator satellite to be launched by the University of Vigo next November through the Russian Dnipro launcher and the University of Rome will allow to check and validate the HumeSat technology developed at the University of Vigo. Once its feasibility is confirmed, the University of Vigo and other academic institutions from all over the world will build the 9 HumeSat comprising the project.
So it was a small error. It was last November, not next November. So we have already launched. So the HumeSat system, this is the mission concept and the constellation. The satellites are going to be launched and integrated in a constellation in order to provide a better system performance. Open international initiative, is absolutely necessary, and this is in this picture. You can see the basic idea. So then we have a very low cost, very simple sensors that you can collect 32 bytes in this version. You are going to send like a WhatsApp, like short message through a very simple modem. And when the satellite is passing over this area, the information is collected in the satellite. And when this satellite is passing over a ground station and we have a communication pass, we download this data, and through internet, we put this data available for the final user. So the concept has been, the performance of the system is going to be, it's necessary to improve the performance to include more than one satellite, because we are using some synchronous orbits. In this case, we have absolutely worldwide coverage. So this is the idea of the constellation. So the space segment, we have a first demonstrator that they have already launched since in 21st of November last year, and we are very, very happy because we could verify the feasibility, viability of the system, and the concept of the storage of forward was absolutely proved. This is the first telemetry just 2 hours after the launch, and everything was nominal. I think we have operated the satellite more than with roughly almost 4,000 commands, and we have made a lot of tests with Spanish and Brazilian sensors. Okay, so the ground segment is standard radio amateur ground segment, and we have in this case, we have operated and we have retrieved all the data through the local station that is in Vigo. In order to improve the performance, I think that it's very important to take into consideration how we are going to, from the legal point of view and from the ITU, we have to think and to do the things in a proper way to avoid any kind of legal problems, to operate and to retrieve data. Otherwise, you know, it's extremely important. So we have had yesterday an extremely interesting presentation by the representative of the ITU, and we have to be, you know, very careful with this. The user segment is very simple. You know, the last release of the last sensor, this is the transmitter, is extremely simple. This is the size of a coin of €1. And we have integrated just in a couple of chips. The transmitter, we can transmit up to 30 dBm, is 1 watt, or including almost 2 watts, we can transmit with this sensor. So I will present an example of resection of the information sent and collected through Brazil, and this is a real pass in Vigo. So we are receiving the signal, and we have in here we have all the data receiver, and we have we have developed an application in the mobile phone in order to deliver and to transmit the information to the final user in an automatic way. So once the ground station has received the data from the sensor, automatically you can connect to the owner through the standard, through your iPhone or Samsung Android system. Is very good. So we are also extremely happy because we have not only one HumeSat satellite, but also the second satellite. And I would like to thank the Brazilian Space Agency and the consortium of the universities to join this United Nations program. And finally, the satellite is ready, and it's a free CubeSat developed by a consortium of universities in Brazil, and is funded by the Brazilian Space Agency. One of the sectors of this satellite provides the compatibility with the HumeSat concept. So this is the idea. There are two sectors, sector A and B, and the sector B includes all the onboard computer and the payload in order to be compatible with the HumeSat payload. It has been included a new important point because we have tested in the first satellite that through using the radio amateur bands, we have detected a lot of interference, and when we were transmitting the information, we included a detection error through the message, but it was not enough. We have included a correction system, and then the performance in this second satellite is going to be much better than we have found in the first. So, for example, in Europe, the performance was not as good as it was in Brazil. So the spectrum was much more clear with less interference, and then it was for us important to improve, and we have scanned all the radio amateur bands, and we have detected different activities and different signals depending on where the satellite is passing over. So this is very important to include not only detection but also correction in the small frames. So it's included, and now the Serpent status is right now is integrating and finally in the AIV campaign in INPE. So we are also very the support from INPE is fantastic, and from LEEDS, the institution, I would like to thank the representatives of Brazilian Instituto Nacional de Pesquisas Espaciais, the support. And what is very important that there are a lot of professors and students of different universities in Brazil has been leading and constructing the Serpent satellites. So it's expected to be launched by the International Space Station. That is good in order, okay, the mission life is shorter. That this was for different launch, but we are not going to generate debris, so they have to balance. And also from the operative point of view, many universities, they are, very, very enthusiastic during the first months, but after some years or some months, the support from the operation point of view decrease, and in some way, launching by the IS, because you have 6-9 months, you can keep, the enthusiasm during all the missions. So we have also deployed some demonstrator nodes. We are working in the radio amateur band with a 32 bytes payload. This is important to have also a license to transmit the data, because we are using the radio amateur band not only in the satellite but also in the node. So it's low consumption, is integration, is tested, and is very good. We have already tested in the Agencia Nacional de Agua, is a water national institution in Brazil, and we could, with the first satellite, we could make a lot of tests, and it was extremely successful. So a practical example, for example, for what they are working in Brazil. So the idea of this kind of system based on data gathering from small satellites is to locate a different ground terminals that they can collect different kind of information and speed of the wind, the water level, the water quality, and through a gateway connects with the satellite and update information when the satellite is passing over there. So you can wake up the sensor, because the system is bidirectional, so it's not only unidirectional. So, and this is an example of a possible application in one of the rivers of Brazil. So there are different possibilities in this system. We have the standard behavior. We can configure the sensor through the satellite. That is very important. If you want to, to increase the data sample that you want to collect the data, or the data array that you want to collect the data, and you can, provide different configuration, and even you can prioritize. And also in an emergency situation, what is very interesting is that you can improve the system through operation, demanding some complementary data of associated sensor that they can be very useful if you detect an emergency. It means it's not only a passive or an active reception, but it's a real set of nerves, of sensors. So this is the idea it's much more for the equatorial countries. It's better in order to improve the revisit time, not to use polar orbit. This could be much more important. But the problem in this case is that there are few launchers that provide low orbit inclination launchers. So this is important. But there are a lot of countries that they could improve the remote observation with less launches, just using almost equatorial orbits. So it could be. One of the application that fits very well with the small satellite are the data collection system, because all of it's very important from the educational point of view, but it's also we can provide some kind of application. We cannot provide set of application because depends of the power, depends of the size of the satellite, but some of them can be provided by small sats. And one of these applications is the collection of data from sensors located in the world. So has been used in very different agriculture, small cities, water management, industry, livestock. So there are many potential applications. That the important thing is these applications are very useful in any country in the world. So you can adapt this sensor to be used for your local application. So it's not only water level, perhaps it's not a problem, but perhaps it's other thing. And nowadays, due to the equipment that we can find, it's very easy to include different heterogeneous sensor interfaces and use, for example, these satellites as a backup transmission if you have, for example, coverage of mobile phones. So I think that is very, there are a lot of things to be done. And just like a presentation, it's a video summarizing a small data collection system.
The fully autonomous system features an enhanced mode of transmission that communicates with satellites while saving energy. Then, all this data can be stored in the satellite or directly sent to the ground stations. The microsatellite solution provides features that make them very convenient for these applications, offering a reliable constellation that beyond redundancy guarantees a non-stop service. The system is managed by the Mission Control Center, commanding the satellite and monitoring the health of the constellation. In case of an emergency situation, these smart ground terminals automatically start transmitting, offering real-time notifications accessible from mobile phone platforms and desktop applications, providing the final user the proper information at the right time, easing the decision-making process.
So this is to finalize my presentation. I would like to thank United Nations to give us 7 years ago the possibility to make this dream in a reality. We have been working a lot to go from the paper to a real satellite, and finally we have already launched one, and in the near future, thanks to the Brazilian cooperation, we are going to launch a second one, and I think that is a very, very good of cooperation because we have a real mission that is interested and fits to a small satellite, and through the participation of the educational institutions, then we can also promote the capacity building, but the students and the professor, they can touch, the results with a very, very nice results. So thank you very much, and it was again thanking for the Mexican Space Agency, for United Nations to give us this opportunity.
Thank you, Fernando, for the very nice presentation. Is there any question from the audience, please? I have a quick question for you. Do you have you been able to collect and publish the data that you collected using your spacecraft?
Yeah. So we have the memory that we have is a quite good memory. It's a 4 gigabits memory.
Okay.
Is more than enough. We only we additionally to the data that has been sent by the sensor, we collect. We have a timestamp, and also we have the Doppler shift. So then, using the Doppler shift, we can also use this system to locate the sensor. So this is very important because if you don't want to include, for example, GPS receiver in order to decrease the cost of the sensor, also the accuracy is not as good as it's including GPS, could be enough for things. And what is good, because it's very, very simple, and now we have chosen the modulation that they are compatible with some mobile systems. The cost of it is extremely cost. So I think that is it's more than enough for the data budget. If we can collect 1,000 or 100,000 of information.
Thank you very much.
You're welcome.
Oh, there is a question?
Hello?
Hello.
Okay. Basically, what you're doing is very similar to what the services that constellations like Orbcom are already offering. So I wonder whether, because the application is very nice, whether you have considered using the existing networks. And the second question is, There has been a very interesting program at the US Air Force lab by Bob Bruniger. They were able to build a satellite similar to yours for about $1,200 material cost. Have you also looked into these designs to keep the satellite low cost? Because I don't know what the cost is of your satellite, so I just wonder.
So obviously there are different solutions, but as far as I know, and you know also, as the price of the Orcon satellites are very, very large, you know. So yeah, the service, and also you can have Argos. You know, Argos is another service that you can send. So then the idea is, sometimes we are thinking about what kind of services can be provided by small sats. And indeed, this service is one of these services. And talking about the cost of the hardware is, I think, that less than 40,000 euros for this 1 unit satellite, including a Gutenberg computer with the memory is Rathar. The FPGA is also tested for its radiation tolerance, so it's quite cheap. So we don't have redundancy. This is the demonstrator, but in order to provide, you know, commercial application, should be improve a little bit the redundancies and the size in order to have, you know, with CubeSat. This is the first demonstrator, but it's standard price for a CubeSat. What is funny is when we are talking about, you know, the cost of the satellites, we never include, you know, the human resource cost, the cost of the people, the facilities, the testing. So this is, you know, we have also to begin to think about this, not only to give just the cost of the hardware, because it's always very, very, but the impact in the project cost is not as much as other different. Thank you. Any other question?
Oh, yeah.
Just as a follow-up question which came into my head is, why do you think the Orbcomm system is so expensive when they're in their third generation of supplying this service?
No, I'm not talking about the service. I am talking the cost of the satellites.
I know, but you're saying that your system is doing a service pretty much
No,
equivalent to what Orbcomm
this is a demonstration
Why
of a service. We cannot compare, obviously, with a commercial service. This have no sense. This is not the objectives of the program. So, but can be evolved to provide commercial applications, but growing the size of the satellites and including some other, you know, things that is, if you want to provide quality of services. So it means Orcom is extremely good, Argos is extremely good, yeah, but they are extremely good providers, so I'm not talking about these kind of things. But the size of Orcom satellites, you know, that they are much bigger, much larger than, this is only my point.
If there is no more question, then thank you very much. Second presentation is with Juan Fernandez Saldivar. And the presentation is on the current challenges in Earth observation systems. I should mention that there is some changes in the sequence of presentation. Presentation by myself and Enrique Pacheco have been moved to towards the end of the session.
Okay. Hello, everyone. Good morning. Probably I'll repeat. My name is Juan Fernandez. I'm today presenting some challenges in high-resolution Earth observation, some of them because it's a wide topic. I'm here representing the Mexican Talent Network. Obviously, we don't have a satellite, but the idea is to see what other professionals in other chapters are doing. The outline of this presentation today, I will give a brief introduction. I'll talk about the requirements, or what most people think they need for high-resolution Earth observation. Some basics in optics, as in what is ground resolution or ground sample distance, what is resolution, what is MTF, and other aspects. Some key technologies that I consider are important for achieving this goal of high resolution, other challenges in these payloads, and followed by a conclusion. Okay, in both commercial and national capabilities, they're demanding high-resolution systems. And normally, everyone calls them high-resolution, but I would call them low sample distance. One thing is sampling, other thing is resolution, but I'll go into that in a bit more detail in a minute. These missions, they often require either very, very tiny pixels, and with mobile technology these days and camera technology these days, pixel sizes, they start coming smaller and smaller. Other technologies is use of back-thin illumination to make the detector more sensitive, use of TDI, where you accumulating charge as you go, longer focal lengths, which brings you a bit of optical design challenges, and big apertures, because the smaller area you see, the less light you collect. So you need a bigger aperture. That's fundamental physics. And in this presentation, I'm going to basically focus on high-resolution push-broom multispectral payloads. This is the main topic. What is one of the major requirements is not only to have something which is high-resolution, but you want to maintain that over the mission lifetime. And of course, the space environment is hostile, to say the least, and you often need to refocus. So this is quite a challenge. The other thing is, you see something in so much detail that you kind of lose a bit of the context. So you really want to have a wide swath, and you want to image for long. So you need a lot of data capacity and downlink. So the more resolution, the more data, the more power you need to downlink. It is quite a challenge. If you want to revisit quite often, then what you have to do is you need to off-point, and that requires a quite agile platform, and that imposes some requirements on the payload as well. I've already mentioned the data rates, and depending on the application, you might need high signal to noise, which again, it depends how you tailor your detector and how you tailor your optics to achieve a certain signal to noise, and ultimately the quality of the image, which is mostly defined by the modulation transfer function, or MTF, which is a concept that I'll explain in a minute. What drives payload development? Well, as most things in space, is cost, because it's not a cheap thing. The other thing is schedule. You really want to keep your schedule short, also to minimize cost. And low risk. You want something that works. You don't want to. It depends on the application, of course, but you don't want to just go around and develop something and you're not too sure it's going to work. You really want something that it's guaranteed. So the question is, how can we improve the payload performance tailored to your application? There's development in technology. I mean, as I said a minute ago, camera technology, mobile technology, detectors, they change all the time. There are newer fabrication technologies in optics. And yes, technology advances, but there are fundamental limits, such as the focal length to achieve a certain ground sample distance for a given detector size, the fraction limit, which is a fundamental limit. So you cannot do anything about that unless you start doing some post-processing enhancement algorithms, and optical aberrations, which again, it's a fundamental physics. So how does this relate to the development of a payload? What really drives? Well, you want to maintain a stable payload, so there's thermal aspects there. You really don't want your camera to be just shrinking and expanding like crazy over an orbit, over the mission lifetime. So you really want low expansion materials. Or you probably want everything to grow in the same rate, so you don't distort anything, except that your focal length might change. And you don't want also your payload to be pointing at an arbitrary location in the ground, so you really want to maintain your pointing accuracy. As I explained before, you really want to be focused. I guess most of us, we've been in a situation where someone takes a picture of us and then you look at it and it's blurred. So if we launch a satellite and you take blurred images, it's unacceptable. It's not that you have another opportunity and say, oh, I didn't like this picture, could you please take another one? Here you have to be focused. So if the space environment is changing your focus, you need to cope with that. Other drivers is you don't want your platform to be shaking like crazy, because again, that will degrade your optical performance, and you want to know where you're pointing. Other aspects is stray light, is light that ends up where you don't want it to be. It could be from a different wavelength, could be from a different point in the ground, and it is quite important. So the challenges, well, there are many areas. There are, from the optical side of things, diffraction limits, that's a given. Optical aberrations, stray light. From the thermal aspects, I've already mentioned a few. Electronics, obviously, you need to take high-resolution images. You need really, really fast electronics to cope with it. Data rates, but also the assembly, and this is quite important as well, because on paper everything looks well. And if you do optical design, you think, oh yeah, I've got it, but it's the tolerancing, the design for manufacture which is important. There's no point in designing something that you cannot actually make. So it is very important to have something you can actually make. But before we say, okay, well, let's have a super high resolution system, what I would like everyone to think is, I thought, oh, we want a high resolution mission for this or that. But is it that you want, or is it that you need? And that's a key, because probably you're going to end up designing something which is over-engineered, which probably doesn't cover your applications, but it just goes too much, and it's going to cost too much, and that's not fair. So I would say first, challenge the mission and application requirements, and it's a good practice. So you can keep the project managers happy. And ask yourselves, what ground sample distance do we want? what sort of swath width we want, because probably you need to add more detectors to achieve that swath, what signal to noise you want, and what MTF or optical resolution you really need. And this is important because most people say, oh, I want a high resolution. Okay, but what signal to noise you want? What MTF you want? I don't know. Okay, well then it's worth have a step back, see what your requirements are, and then go back to the drawing board. With that, I think I've just showed too many words. I'll put some images. The basic concept. So what is field of view? Well, field of view is an angular, it's the angular extent of what the imager sees. What is ground sample distance? Well, it's the projection of a pixel in the ground. That doesn't mean you have the resolution to see that pixel. It's just a geometrical construction of your pixel size on the ground. And swath is how much you cover. So on this slide, you have a pointer. You have a high resolution spacecraft where a single pixel covers this ground sample distance. Okay. Yeah, okay. So the projection of a pixel in the ground refers to the ground sample distance. The swath is how big the whole detector is. So the detector could see all that extent. A single pixel would be that. Sorry for my shaky hand, but it's difficult to point a laser to a single pixel. But you can see the blocks there. That represents a single pixel. Bear in mind that the spacecraft is traveling at 7 kilometers per second. Just to give you a bit of a context, this is 25,000 kilometers per hour, and you try to image, let's say, a meter in the ground. Obviously, it depends on your orbital height, but it's basic geometry. So your triangle that defines your pixel size corresponds to your ground sample distance, and your detector length corresponds to your swath width, and your orbital height will be related to your focal length. And if you want this to be small, what do? Okay, well, you can have a very small pixel, you could have a very long focal length, or you can fly lower. But if you fly lower, you're probably not going to stay high for very long. So you have to keep that in mind, your mission lifetime. Ultimately, the aperture doesn't have a play necessarily in the GSD, but that's what's going to determine how many photons you collect. So you cannot just don't think about the aperture, because it's a fundamental. A point in the ground will be only a point there if your aperture was infinite, and that's the diffraction limit. A point there will be a point there if that's infinite, and there's no infinite aperture. So the size of that point will be a blob, and that blob is determined by how big the aperture is. The bigger the aperture, the smaller the blob. Again, bear in mind that the spacecraft is traveling at 7 kilometers per second, so you have to take a picture very, very quick in the microsecond regime. So it is quite a challenge. But before you start thinking, okay, well, I want something super high resolution, super fast, how much ground sample distance do we need, and what difference does it make? You could have a system with half a meter, or you could have a system with 1 meter. That generates 4 times the volume of that. So you need to cope with that on the spacecraft. But for some applications, is it or is not strictly required? I'm representing here the same area in the ground scaled to different ground sample distances, and if your application was, for example, counting the number of planes, you can count the number of planes there, as you can count the number of planes there, as you can count the number of planes there, as you can count the number of planes there. So why go for one as opposed to the other when one costs much more? Or probably you need what? Double the focal length? So if you double the focal length, your volume is going to go by the cube of that. So you have to keep these relations in mind. You cannot just say, oh yeah, I want super high resolution and whatever the focal length. No, the whole thing is going to scale to the cube of that. So it is very important. And that's sample distance, which is completely different from resolution, which I explain here in a minute. As I said before, a point will become a blob. If you have good optics, you will have most of your energy contained there. But if you have bad optics, and by bad optics I mean optics that probably distorted, that probably not well polished, that probably they have some thermal aspects associated with it, and then your energy is going to start spilling over neighboring pixels. So if you have a good system, you will see something like that, and I hope this screen gives you an idea of how blurred that looks. And again, your pixel size is the same, your focal length is the same, your optics are not the same. You need to really make sure you nail your optics and your mechanics to achieve that. And the key is what is sampling, what's resolution. So what would you prefer, having a low ground sample distance, high, well, low as in smaller ground sample distance with a low resolution or modulation transfer function, or MTF, or probably you want something not as high or as low ground sample distance, you want high resolution. This is really what high resolution means. So what would you want? You probably want something in the middle, or probably you want both. Again, it depends on your application. So please step back and think of what exactly your high resolution mission requires. How much signal do you need? Because the focal length will give you your ground sample distance, the quality of the optics will give you your resolution, but how many photons are you collecting? That depends on your aperture. If you collect many, then you have a good signal to noise. If you don't collect those many, you have a low signal to noise. But again, for some applications, again, if you're counting planes, it might not make much difference. But on the other hand, if you're doing any scientific applications where NDVIs and other imaging products are into play, you have to be very, very, very careful about your signal to noise. What defines the signal to noise? Well, many other things, including the detectors. There's two main types of detectors. There's CMOS and CCDs. I'm not going to get into technical details on each. But you need to choose the right detector. That's where your design starts. So you really need to know how your detector performs, how much photons you can collect, what is your noise performance, linearity, and so many other aspects. Some of them that can be taken into account, such as PRNU, PSNU, that you can probably calibrate out. So that's not going to show in your picture, but you really need to know how they behave so you can have appropriate strategy to do it. If you want more light, probably you want a detector with higher quantum efficiencies or responsivities. And again, if you're going over the ground at really, really fast speeds, probably what you want is you want to add as much signal as possible in what it is called a TDI, or time delayed integration mode. And it's key for high resolution. But again, probably you don't need only one detector, probably you need many, and then your optics are complex, then your focal plane is more complex, and what you often do is you just put mirrors, and then you send the signal to one side or the other side, and you put CCDs or detectors on opposite sides, but it's quite a complex arrangement. The bigger the swath, you probably need many more CCDs. That's going to be a larger focal plane. It's going to dissipate more power. It's going to basically have a quite stringent thermal issues. Other examples of focal plane assemblies, it could be as simple as that, or it could be as complicated as that plus the filters. So it can be quite tricky, because then now every single detector you need to align, everything needs to be coplanar, otherwise one side of the image will be focused whilst the other one isn't, or it could be just distorting. So you have to be very, very, very careful with that. You need to choose your right detector, you need to have a good strategy for your focal plane, and you need to choose the right materials. You want something that doesn't expand, or that expands at a rate that you know. Some typical materials are listed there. I'm not going to go in detail, but you want something with high thermal conductivity, low thermal expansion, and you want something that it's light. The lighter it is, then your launch and everything is going to be much more affordable. I mentioned about the fact that sometimes you go and take a picture and it's out of focus, so you need to cope with that in orbit. And it's always tricky to put mechanism in space, so you really need high-resolution mechanisms. And again, thermal aspects are also key there. So it is quite a complicated thing to do. Other challenges, not only materials, not only focal plane detector technology, is vibration. You have reaction wheels, 3-axis stabilized or whatever, but those are going to probably induce some vibrations in your spacecraft. So you have to keep an eye on that. The data volume you generate is enormous. So you also have to have good strategy to cope with that. Metrology, you have to be very, very careful about how you measure and you maintain your optical alignment. But the most important thing, as I see it, is there's no point in designing something you cannot achieve. So you have to make it to know that it works, and that's the moment of truth. So when you start aligning things, and just to give you an idea of the scale of what small satellite can do sometimes, you have to be very, very careful in your AIT, or assembly integration and testing facilities. It is not an easy thing to align something to that sort of precision, nanometric precision, micron precision in some aspects. And with that, I would like to conclude my talk. Basically, I want to convey the message that high-resolution payloads are quite complex. It's not just, I have a smaller pixel size, I just increase my focal length. There's a bit more than that. You have to be conscientious. You have to really analyze your requirements, see what is that you're trying to achieve. Not just say, I want a high resolution and that's it. You're probably going to end up with something which is, it's not what you need. One thing is you want, the other thing is what you need. It's going to be complex. It's not easy. So complex focal planes are most of the times required, and you have to stay focused, as I mentioned before. And there's so many future areas of interest that I've already covered. But I would say that the most important thing is to make it happen, to actually build it. And with that, I would like to conclude my presentation. I would like to thank the United Nations and the Mexican Space Agency for supporting and for this great opportunity of being here. CICESE for the great facilities and for all the logistics. Sobre Satellite Technology, which I work for, but on this occasion I'm not presenting on their behalf. You already had St. Martin's meeting, so I cannot compete with that. CONACYT for being the sponsor of my studies. The Mexican Talent Network and the Mexican Embassy in the UK, which they've been quite supportive for me being here. And I would like to thank you all, and also my family, which I think they're watching over the internet. Thank you very much. I don't know if there'll be time for questions now or later. Anyway, I'm happy to...
Yeah, we can probably, thank you, Juan. We can probably take one question or 30 minutes.
Yeah, I mean, I can take as many after the session, but for now, it's okay. Yeah.
Any question at all?
Okay.
So maybe they're shy, so...
Yeah, thank you.
Thank you.
Thank you, everyone.
The next presenter is Matt Daniels from NASA Ames. And Matt will discuss the Earth orbit infrastructure with small satellites.
for long-term missions. Good morning, my name is Matt Daniels. So I'm interested in when we might move for long-term Earth orbit projects from large satellites to groups of smaller satellites and new international collaboration opportunities that might create. And how do I go through this? Next slide would be great. Yep. Nope. I'll do a dance on the side while you... What'd you push? That, thank you. Okay, so I give a lot of talks as well to groups that are sometimes not purely space people, so I expect that this group will know this, but usually the way that I start a talk to a very diverse group is I remind everyone that space capabilities go into an enormous number of terrestrial applications. So GPS alone, position, navigation, and time systems, go into not just position data, but the timing signal goes into a huge number of applications. There's a large number of commercial applications, national and international scientific applications, and of course a long history in national and international security. So many long-term American projects in Earth orbit use this approach right now. We build very large satellites. They tend to be very long-lived. They tend to be extremely expensive. And I'm interested in when we might replicate the capabilities of these very large satellites with a group of smaller satellites. This could be anywhere from 2 to, let's say, about 5 satellites. And for convenience, and to be a little bit more precise about that, I'm going to talk about separating the payload capabilities that normally reside on a large satellite onto a group of heterogeneous, so different, smaller satellites. So the idea is we're not putting a bunch of clones up, we're putting a group of, say, 4 or 5 satellites that are each different from each other and collectively emulate the capabilities of that bigger satellite. And for convenience, I'm going to talk about the big one as a consolidated system and the group of smaller ones as a distributed system. So backing up as well, it helps to just distinguish why a single space project, so one particular project, might use multiple satellites. One reason is a physics-based reason. So if you have a physical requirement for multi-point operations simultaneously in space, then you need multiple satellites. So GPS is a prime example of that. A second reason would be coverage and revisit reasons. So if you wanted to fly over particular parts of the Earth more often, you might put clones of your satellites up and then have more satellites in orbit. That's probably the most common one. The one that I'm interested in, though, is when you might use multiple satellites in a case where you could use just one satellite, but where you get some kind of value increase or operational advantage or better management of risk by using multiple smaller satellites instead. And to be really specific, we could actually use as an example a sort of large modern weather satellites. This is the NPP satellite. It has 5 primary payloads. Conceptually, at least, you could imagine that we could put these payloads on any number of satellites between 1 and 5. There's some technical things that go into this, but let's abstract for a moment and say that that's the case. So the question then is, how would you decide to do that? We chose for this particular satellite to put them all on one spacecraft, but why might you use multiple satellites? There are a few families of potential benefits that you can get. First one is when things fail in orbit. This happens sometimes. You could respond to failures more cost-effectively and more quickly if you're just replacing a smaller increment of the system, if you're just launching a smaller satellite. This might also mean that over a very long program, so over 20 years, you might actually get more, we call it replenishment efficiencies. So if I had a large satellite that has several critical payloads, and I say that some subset of them, let's say 3 of them, have to be working at all times. That's just the definition of the program. If one of them fails, supposedly I'm going to launch a new very large satellite to replace that one failed component. So over 20 years, maybe I could just launch sort of more efficiently the parts that I need when things fail. I could launch incrementally, so I don't have to wait, hypothetically, if one payload out of 5 is delayed for several years, I don't have to wait until the last one is ready. I could go ahead and start launching the other ones and start getting benefit. And it might actually be useful for upgrading technology. So if my payloads improve year over year, it might be easier and more effective to gradually deploy new technologies into orbit by using these smaller satellites, rather than having to recapitalize this entire very large system. So that's why you might use multiple satellites. I actually do research on this, so we do quantitative modeling on this. And part of what I want to convince you of very quickly is that there's a very sensible reason, set of reasons why the United States might move in this direction for certain missions on a case-by-case basis. To build these quantitative models, we think about an organization that derives value from satellite data. In our research, we usually call it the firm, because if we say the agency, people think we're talking about the CIA. And if I say the company, people think I'm talking about the CIA. So we say the firm. The firm could be a government agency or a large private corporation, but we're going to say that this organization does three things. It buys satellites, which is actually how large organizations work. They don't, NASA and the Air Force generally contract out the construction of satellites. So we're going to say that we buy satellites from someone else. We're going to operate the satellites, though, and we derive value from producing data. So we pay for the satellites, we pay to operate them, and we get value from the data. And what we want to analyze, so I'm going to go over, I'm going to step over some of the quantitative details for the models, but generally what we want to analyze is how would we make a decision between this type of consolidated satellite system or a distributed system, as I called it before. So we build quantitative models that are based on optimization and simulation, and the general idea of what we're doing is actually we think about these trade-offs that you face over a long-term program. So if you're going to run, let's say, a weather satellite program for 20 years, there's a whole set of trade-offs you make about when you buy satellites and when you launch satellites, whether you keep ground spares or in-orbit spares, how soon preemptively you launch replacement satellites. So we're going to do a full optimization on that entire strategy, because it turns out that a distributed system might actually have a different sort of optimal way of using the system, a different concept of operations than this big consolidated system. And then we're going to compare the value of each one given this best strategy for using the system. And the format of the results, not everyone is familiar with this, but we want a way, at least for the quantitative people, to look at results in a very detailed way. And so the way that we do that is we're going to have a distribution on value. So this is a probability distribution. And imagine that I'm going to put the benefits that I get from a system, the value of data, into the same units as my costs. And then there's a lot of uncertainty in the 20-year satellite program, so things could go very well, they could go very badly. It could be somewhere in between. We want to look at what the distribution is on possible outcomes over that 20-year program. And I'm also going to talk about something called risk aversion. And when I talk about risk aversion, I mean actually a very precise economic concept. I'm going to talk about how sensitive are you, when I say risk aversion, to low probability bad outcome scenarios. So if something is very unlikely to happen, but is very bad if it does happen, how much does that weigh into your thinking? Sometimes a little bit more than others. I'm actually, for the sake of time, I'm going to skip that one and go actually to real results. So two very high-level results that we get from quantitative modeling to kind of motivate why the United States might think about moving toward smaller satellites. We're going to look at a reference, we call it a reference geostationary mission. So we'll look at a large satellite in geostationary orbit and compare the most simple case that we could come up with. Essentially one big satellite that we're going to try to maintain in a particular geoslot for 20 years to a pair of satellites. We're going to divide up that big satellite into two smaller satellites and then manage that for 20 years instead. And the first thing to notice is, and this is actually remarkably consistent across different mission types that we analyze with this, is these consolidated systems tend to be very likely to do quite well. This makes sense. We actually build large satellites. We spend a lot of money on it, and we make them highly reliable. So we put so much redundancy into them, we should kind of expect this. We should expect that if you invest that much money in a single satellite, it's likely to work. Thing is, though, these consolidated satellites also have a longer left tail. So if things go badly, it's possible for things to go really badly. It's possible for your system to break, and then it takes a long time to build a replacement, and the replacement's really expensive, and you have a gap of data. Distributed systems tend to have a smaller left tail. So the first thing that's been interesting to notice, I think particularly for the space community in the United States, is that we think of, if you're risk averse, you build big satellites, because on a big satellite you have room for redundant subsystems and redundant components. So one of the results that's coming out of this is it turns out if you are very risk averse, you might actually prefer a distributed system that is composed of smaller satellites that are individually shorter lived and that individually might be less reliable. Kind of neat. The second thing is technology advancement. So if technology is changing year over year, quickly. So if you say that we could imagine a couple of different scenarios. One is where technology never changes. We're just always going to launch the same cameras and the same payloads in orbit. There's one scenario. A different scenario might be that technology changes rapidly year over year. So if you buy a new camera 4 years in the future, it might be a much better camera. If that's the case, it turns out distributed systems built on these smaller satellites tend to be able to capture those benefits much more effectively. And I'm happy to go into details about that in Q&A, but bottom line is that if technology changes a lot year over year, you can actually capture those advantages perhaps a lot more effectively with these distributed satellite systems. Kind of neat. So that's why the United States might think about, for some really significant long-term capabilities in Earth orbit, like national weather satellites, moving toward distributed systems. This is something we are going to be thinking about for probably the next decade. Neat thing, though, is right now, with these large satellite systems, so let's think about how we can collaborate internationally. Right now, with these big satellite systems that are long-lived, that we put into orbit, there are a couple of ways to collaborate if you want to collaborate on the space segment. There's a lot of stuff that we can do between scientific ministries and between space agencies. But if we want to collaborate really on the space segment, there's a couple of things that we can do. So we could share data. We could come up with an agreement where perhaps ground stations in other countries could receive data from our satellites and vice versa. We can receive data from their satellites and then we trade data. We could also swap instruments. So we could say that we'll host another country's payload on an American satellite, or again, vice versa. If we move toward these distributed satellite systems, one benefit is maybe in the years ahead, we could think about multinational satellite constellations. So now you could think about not just sharing payloads, but we could go ahead and launch the systems that we need, the payloads that we need. And we could say that if somebody else wants to join that constellation, they can launch a payload into it as well, and then we'll start sharing data as soon as it's up there. But we don't have to wait. This is also different from the International Space Station. The International Space Station, you have to kind of wait until everyone is at a certain point. Everyone has to progress kind of at the same rate, or it doesn't work. This is neat because you can go ahead and have some countries deploy things, and other countries can deploy systems as they become ready. There's one more part about this, the last thing that I kind of want to leave you with, is how do we think about this in the long term? So there's a neat technological idea here in the long term. If we think about maybe 5 or 10 years from now, moving toward these types of constellations, it also makes sense that we would start to design our satellites to reflect the best designs for these constellations. And we might, at some point, say, what if instead of just launching these different payloads up to join a constellation, we actually put a satellite into each constellation that is specialized for a particular thing, like high bandwidth downlinks, or computing on orbit. So now, maybe in this limit over the years ahead, we can imagine that we from NASA could go ahead and launch just a payload into a particular orbit with a sort of minimal downlink capability, but the ability to wirelessly transfer data to another satellite in orbit, and that other satellite would beam it down. It would be a bit like a cell phone and cell phone tower model. So you could begin to imagine Earth orbit or near Earth space broadly as more of a software environment. Deploying a satellite into near Earth space is more like adding a node to a network than launching a sort of self-contained satellite that has to work entirely on its own. So in the long run then, you could imagine thinking of near Earth space as more of a software environment than a hardware environment. I'm going to leave you at that, and I'm happy to take questions. Yes?
Question, yeah.
I can hear you, so.
Hello. Good morning.
Good morning.
From your point of view, what is the size and the mass of a small satellite that could be achieved, these kind of missions?
Right. So I was trying to not specify that a little bit. So the idea is some of the things that we're looking at right now is how we would replicate the capabilities of very big satellites. So these are over 1,000 kilograms, massive satellites, with groups of what could range from small to sort of medium-class satellites. So I would say anywhere from 100 kilograms up to, let's say, a few hundred kilograms, like 300 or 400 kilograms. Small or medium satellites. Not nanosatellites, not microsatellites, but small satellites. And that's largely a function of there are certain payloads that we, certain instruments for things like weather data products that we want to use consistently. So it's, they still just come in sort of large form factors, and we would need to accommodate those still. Yeah?
Hi, I'm Ariel from Israel. This was a really great presentation in different point of view. One thing I would like you to elaborate a little is I saw on the graph there that it really does make sense that the tail cuts down with when the low probabilities of things getting really bad, because you actually distribute the risk between the satellites. But I would intuitively I would expect the right side of the graph also to centralize, because the risk, the chances of everything to work perfectly also kind of decrease. So, and I was surprised that actually the right side also you have like more probability of a high value venue. So can you a bit elaborate on that side?
Yeah,
exactly, this is the graph I meant to.
This one. So this one, let me check one thing briefly. I want to see if I put other distributions in. Nope. So I can talk to these. So the thing that you're seeing here, so the thing you identified first of all is a key idea. So the probability with a distributed system of having small failures is higher. And so the interesting trade is if you're very risk averse, that's a preferable trade. You would actually rather make a system that is more likely to have small failures but very unlikely to have the sort of catastrophic scenario than the alternative. In this particular case, it gets a little bit higher because it can actually realize new technologies more effectively. So that's what you're seeing in this particular model run. So this is with a sort of incredibly small technology advancement rate, but it's saying that with a large system, you're more locked into existing technologies, and with a small satellite system, you can actually kind of get out a little bit better. It's not hugely likely, but one possible outcome is if everything works, you could actually have a system that works as well as your consolidated system, but sort of inserts better technologies over the course of a 20-year program. Thank you. Anything else? Okay. Thank you.
Thank you very much. We have Saul Santillan, I hope I get it right, and Saul de la Rosa as our next presenters, presenting on the satellite Condor.
Okay. Good morning. My name is Saul de la Rosa from the National Autonomous University of Mexico, UNAM. We will show you the project Macrosatellite Condor UNAM MAI. Thank you. Well, this project is under the frame of collaboration between Mexico and Russia. We work under the program of technical and scientific cooperation Mexico-Russia, academic collaboration agreement between the National Autonomous University of Mexico, UNAM, and the Moscow Aviation Institute, MAI, and with the agreement for the implementation of the project Satellite Condor. We have several objectives. One are the academic objectives. We want to consolidate the space technology work group at the UNAM, also to build and strengthen academic ties between participating countries. Also, we have technological objectives. Develop a multi-mission microsatellite and also collect information on board the satellite for the study, the ionospheric precursor of earthquakes. Also, one of the main objects that we have, it is very interesting for us, for Mexico, is to test a remote sensing camera designed in Mexico, in UNAM. Well, some goals about UNAM. What is UNAM? The UNAM is the educational, scientific, cultural, and social project most important in Mexico. Inside of UNAM, the School of Engineers is carrying on the satellite project. The School of Engineers of UNAM has been and is the leading institution in the training of professionals engineering in Mexico. Our experience in space. The satellite UNAMSat is the first satellite made in Mexico, in UNAM, which operates in space. We participate in this project. This is our heritage. About our main partner in this project, the Moscow Aviation Institute. MAI has special faculties that cover all the specialties required for develop any space program. Also, we have cooperation with other entities. For example, NP Laboshkin. Laboshkin is one of the Russian leading companies in the development and practical use of unmanned spacecraft for space exploration. Laboshkin supports the Condor project with the basic satellite platform, instrumentation, assembly, and tests, also training and engineering model assembly in Mexico. The National Central University of Taiwan, also all other support. This university, his Institute of Space Science, provides the instruments for the pilot to study the ionospheric plasma. This is all the entities participating in Satellite Project Condor. Also, we have the participation of the Benemérita Universidad Autónoma de Puebla, and other entities, also the Institute of Geografía of UNAM, and the Centro de Geociencias UNAM. Well, about general requirements, cost of these satellites is less than $1 million. Duration of implementation is the integration, must be less 2 months, 12 months. Lifetime that we're expecting will be more than 1 year, and also, will be payload from Mexico and Taiwan. These are some of the key technical parameters. This is a microsatellite, around 50 kilograms, power between 50 and 80 watts. We will transmit an S-band, our telemetry, scientific telemetry. We will be in low Earth orbit, almost 600 kilometers. This is a view of the satellite, view of the pilot of the satellite, about the stage of the development. This is a long project because we have a lot of goals. The main is to prepare engineers in this area. But well, right now we are in the stage 4. We are in the satellite assembly in Russia, and also we will provide space qualification tests of the pilot with the boost of the platform, satellite platform. We expect to launch at the end of 2015. Also, for us, it's very, very important right now that in the High Technology Center of UNAM, CAT, we are designing and construct the remote sensing camera that will be the pilot, one of the pilots of our satellite. Well, the culmination of the satellite project Condor is not just to launch the satellite. The main purpose is to consolidate the group of Mexican specialists in UNAM in order to develop the space technology in Mexico. UNAM is consolidating the High Technology Center of the School of Engineering in order to integrate the Mexican specialists in Mexico and to create the laboratories for continued work with the cooperation with international institutes like UNAM or others. Now, Dr. Santillan, chief of this center, will talk you about the High Technology Center.
Well, just to finish this one, as Saul pointed earlier, the work on the Condor has helped us to attract another two missions. This is Ulysses, that is a nanosatellite that is made for artistic purposes and use. And this is Quetzal, that is another project that we are at this moment working on the earlier stages of the process, and with the help, of the CONACYT, we are setting a network with other institutions in order to collaborate and foster development here in Mexico. And also, we are working in establishing a joint graduate program. So those are the byproducts of Condor, and as you can see, the idea was not just to create a program for a microsatellite, but it was also the beginning, in collaboration with the Space Agency from Mexico and other institutions, to start working in a more comprehensive academic and also research system that benefits all the country. So that's the real and the most important part of Condor. That is what like the kickoff for us to start working with this and in a more comprehensive fashion and with a unifying vision with other institutions of the country. Thanks for your attention.
Thank you very much, and I would like to welcome questions from the audience.
Good morning. That's interesting project. I would like to know what is, when the satellite goes around the Earth, what would be the projects, or what will be the sensors, what will be measuring, I don't know, pollution, temperature, what will be next?
The mission is to test a theory about earthquake precursors, making disturbances in the ionosphere. But also it has the plus that several of the ionospheric events affects communications and affects other systems, especially in transmissions for different bands. So it's very important for the Taiwanese, for the Russian, and for us to check on the earthquake theory, because if this is true, we can have a 48 to 72 hours warning in advance of a big earthquake. Even that this is not true, the capability of measuring the ionospheric phenomena and their effects over telecommunications makes that the scientific purposes for the satellite will be fulfilled. So this is one of these win-win situations with the three parts are going to collaborate and get something in benefit.
What is the payload for the ionosphere earthquake?
Langmuir probe and magnetometer, and also plasma temperature measuring device. Any other question? Thank you very much.
Thank you very much. Next, we have Enrique Pacheco from the Mexican Space Agency to discuss the small satellite program for early warning systems.
Thank you, Mr. Chairman. Thank you, everyone. It's a great pleasure to have the opportunity to talk a little bit about the work that in the Mexican Space Agency we are trying to conduct in terms of this very important topic that is related with early warning systems. As Dr. Mendieta mentioned during the keynote speakers session at the beginning of the workshop, the Mexican Space Agency is trying to address two main goals: social needs and how to foster and develop a space industry that can produce wealth and progress in Mexico. So I am going to try to explain a little bit more about how the Mexican Space Agency is trying to address the social needs related with early warning systems, and how we can expect to contribute, because the early warning system in Mexico involves several entities from the federal government, from the state authorities, from the municipal councils, in which everyone have a special part of the problem to deal with. But now that the Mexican Space Agency is in operation, we are under an excellent opportunity to provide space technology and space images in order to help all these entities to have better information that can help to take better decisions and quicker decisions in terms of early warning. So I'm going to take some slides trying to describe what is the current situation related with the early warning systems in Mexico and disasters aspects. Let's go to talk a little bit space infrastructure, that also was a topic that Dr. Mendieta introduced before, and how we expected to address the social needs on the future. So, as you know, probably Mexico is a very vulnerable country related with the natural origin disasters, and we make we have the saying that except a snow avalanche, probably we have any other kind of disasters in Mexico. So there is no. We have a big country, and each part of the country have a particular issues related with disasters. But we have hurricanes, earthquakes, forest fires, droughts, tropical storms, even we can be exposed to pollution-related disasters like oil spills, volcanoes, etc. We have really a lot of situations that involve exposure from the Mexican inhabitants to any different kind of disaster. So, as you can imagine, the monitoring aspects related with disasters is a challenge, but also we saw that as a big opportunity to provide an integrated system to provide innovation, to provide resources in terms to deal with this aspect in a much better way. But let's go to be honest that it's not a problem for a single country. The aspects related with disasters is a global challenge, and we need to deal in a global scope with these aspects. So Mexico is also have a strong commitment in the international community to collaborate and to participate in terms of contributions of aspects related with the environment care and CO2 measurements, security, even space debris and space weather. So we are one of the very few countries that have a national law in which astronomical disasters are considered part of the disaster civil law. And the Mexican Space Agency now have the responsibility to establish monitoring and protocols to deal with disasters origin from the space. From the point of view of our national needs, we don't have any domestic satellite related with the remote sensing. We have a lot of communication satellites, but we don't have any remote sensing satellite that is part of that is owned by the country. So we relied in international cooperation and international source of images, but at the end, these satellites could not be designed exactly thinking on the needs of Mexico. So not the orbit, not the revisit time, not the spectral capabilities. So we need to think. We detect this as a lack of situation for Mexico. Also, we have limited availability. Not all the images are available in the moment that we need. So we need to also deal with that aspects. And there is some issue related with intellectual property, because normally we have the license to use the images, but not the property of the image. So this prevents that, for example, some part of the federal government can rely on the private sector to produce additional products based on these images. And at the end, this is a constraint that is limiting the capabilities and usability of this remote sensing data. From the point of view of national security, at the end, is a matter of that we depend on foreign assets, and this is some kind of particular. In the global aspects, we have some challenges that we need to deal with, and these are, from the point of view of our country, economic and organizational. So from the economic point of view, we need to deal with the political aspects in which these kind of space projects normally take a long time, several of them, and the cost of the project are big. So we need to start to think in a different, out of the box, and not to rely only in the government as a sole source of funding, because this has been historically the way in which these projects has been conducted. And we need to overcome the necessities of and short-term vision in terms of political aspects. And this federal administration, for the very first time, has provided indications and signs that as the president is saying, Mexico is taking the challenge to change. And from that point of view, we can see that recently was announced a new airport for Mexico City that is going to take several years to develop. But this administration is assuming the challenge to deal with this investment, even if they are not going to take the political opportunity to take the end result in their hands. So they are thinking in a way in which the space projects looks to fit more natural to this way of thinking. From the point of view of organizational aspects, we need to deal with management, that is management skills mainly, because the space projects requires particular management skills and system engineering, aspects that we need to develop on the country in a better way. Also, we need to improve our technical knowledge. Dr. Mendieta said we have a basic space science very well established on the country, but we need to deal with technological know-how in order to improve our capabilities in terms of space. One political aspect that we improve a lot is the concept of a space infrastructure. We managed to convince all the decision makers and most of the society involved with the political decisions and economical decisions and technological decisions related with the space, that the space infrastructure is at the same level of importance that roads, that airports, that harbors, and that we need to think on the space in this long-term vision. We need to deal with the space as a space infrastructure that is going to support the economical growth of Mexico. From that point of view, has been really, really important that for the very first time on the National Infrastructure Plan, that is the main planning of the government related with the infrastructure, we already have there the development of remote sensing satellites and spaceports and launchers. So as a way to think on a space infrastructure for the future. And also, for the very first time, the space is play a significant role in the sectoral planning of the Ministry of Communications and Transport, in which the agency is part of, and a way to deal with all the development of space capabilities and space infrastructure to solve the social needs of the country. So we are trying to develop science and technology in order to construct these national capabilities and capacities to support the development of the future projects. And for that, we are using small satellites. Small satellites has been the neighbor to us to start to conduct technological projects at low cost in order to gain and to put all the pieces together to have these national capacities under development. And the main goal, of course, is disasters, how to construct and how to provide information in order to improve the space information that the government is getting related with disaster management. So we expected to propose, and we are looking the funding for to have 2 satellites, as Dr. Mendecia mentioned. One is high-resolution image satellite that is going to be disasters and one of the aspects, and also a medium-resolution satellite. So this system of 2 satellites is going to come together with a national ground infrastructure that is going to be a national data center, better connectivity, data processing facilities, in order to have all these national key infrastructure that is going to support the capability of Mexico to produce end products for the different users, starting with the federal government, but of course trying to support another entities like research facilities or private sector also. So more or less this is the scope of, to have the 2 resolution, high resolution and medium resolution with thermal sensors. We expected to develop this in 3 years with the international collaboration, of course. And we expected to have a 7 years lifetime of the satellites, and the idea is to conduct and to grow this ground infrastructure in the country. So this National Center for Storage and Processing, not only geomatics that is a key, but also astrophysics that has, as you are here in a town very close to one of the biggest national observatories, and one of the 4 remaining places in the world that are capable to have optical observation on the visible range mainly. And the idea is to develop this storage center to deal with all the archive images that already we have on the federal government, but also to start to get in that place all the images that the federal is acquiring from different sources as a starting point. And we expected to have this probably for the first quarter of the next year up and running. And already we have the connectivity between the federal entities up and running. So this is going to be one of the first way to start to use in a more efficient way all the geomatics information that the Mexican government have in place. Also, we expected to have small satellites as a technological demonstrators in the near future, very close, in order to start to gain all this knowledge related with the big satellites that we expected to develop in the coming years. Of course, human capital is a key and fundamental aspect. So we expected to continue to support the growing and interchange programs related with human capital. And we are focused in trying to develop some expertise in particular key areas that are related with the stabilization, control, all the necessary knowledge to point properly the satellite on space, but also we develop here capabilities to remote sensing devices and other areas of opportunity like optical communications or radio frequency, high frequency devices. This is some kind of path in which we are working as a technology roadmap to gain experience and to develop capacities. You are having the opportunity to see some of the researchers telling you on first hand how they are dealing with the research activities. And we, for example, have the opportunity to listen to Gustavo Tanco about the stratospheric balloon and how successful has been this as a first truly scientific cooperation between NASA and Mexican Space Agency. Also, you listen the highly contribution aspects related with CANSATs, the CubeSats that are underdeveloped. You listen the Condor project already as a important aspect. All these programs has been supported and are continued to be supported in some way or another for the Mexican Space Agency. And the idea is to continue to have these projects running now that we are established the trust between the national science body and the Mexican Space Agency to continue to provide funding opportunities to deal with all these technological developments. And this is an example of picture related with the development that we have in place. And this is one of the ideas that we want to leave. The only solution to deal with all these global challenges that are particularly important for Mexico related with disasters is, from our point of view, cooperation. And we need to establish that cooperation between the space nation that already has a long tradition, but also all the Latin American and all new nations that are starting to develop capacities in the space sector, because the innovation coming from the necessity in some way. So these countries that have a lot of necessity as providing a lot of innovation and novel ideas that together with the expertise and experience of other countries, I think that we can have a truly equal relationship between the countries that can provide an advance how the humankind is dealing with this global challenge. So the example for us is that image sharing coming from several countries, and how do we propose to have this collaboration, for example. And this is one of the ideas that we want to leave on this for the discussions as a wrap-up of the workshop, and is how we can support initially networking between Mexican and Latin American researchers, how we can make a stronger our region in terms of collaboration links, and of course, several of the issues that prevent this collaboration normally is funding. This is why we are working so hard to provide all the researchers, Mexican and Latin American, funding opportunities to link together, to work together, to establish joint projects together in order to have the opportunity to produce results. And these results are going to have an impact on our countries and our needs, and this is going to be a big snowball that is going to, with better results, we are going to get more funding and more opportunities to collaborate. And of course, the idea is to provide this networking of region researchers working together as a contribution to the international community to participate in space programs and missions that help us to deal with the global challenge. So we are going to offer grants. We are establish the mechanism to offer grants to support the participation on all these researchers that can produce a paper for the conference in 2016 in Guadalajara, but not just a single location aspect. We are going to establish a mechanism that is going to help to start in 2016, but to continue to participate every year on that conference as an example of participation of the region and our activity in the past. So let's go to invite all the researchers let's go to take advantage of all these networking opportunities that have been during these days to try to establish links and feel confident that from the Mexican Space Agency point of view, we are more than happy to support all these links and all these connections in order to produce results. And again, make the remark that we expect them to have, if you already try and try the flavor of Mexico here, expecting the full culture experience once that you were in 2016 Guadalajara, birth of tequila, mariachi, Mexican food, and all the aspects related with that. So, as a summary, let me take that from our point of view, the Mexican point of view and Mexico experience, building a space infrastructure as a concept has been a big change of mind. And we invite to consider and work together with us in terms to convince our different communities that the space infrastructure need to be deal with this kind of vision. It's an important as an airport, as a harbor, as a roads. Also, we already identified that capacity building needs to be addressed as a key priority for our region, and particularly for all the countries that want to develop capacities in their own countries related with technology development. And for Latin America, both aspects are really important. How to deal with disasters in a global scope, and how to develop these capacities to support the growing or our space activities in the region and in the world. So thank you so much for the opportunity. Thank you, Mr. Chairman.
Is there any question for Enrique?
Okay, so when you run through your presentation, can you explain any grassroots level applications that you're looking at using? You talked about building space infrastructure as such, but considering the profile of Mexico, can you explain any grassroots level applications?
Yes, for example, we are thinking to start to generate different kind of products at the end. So, for example, now we have images, and these images at the end is not valuable if they don't have the layers of information required from the different entities and the different levels. So, we are dealing now with identify the needs of every particular entity in Mexico from the federal government, and with these needs, we are to try to develop the right products on the processing aspects in order for them to take better decisions and improve decisions related with the space imagery. For example, radar in Mexico, we are not processing radar images. We are getting end products as an aspect, but we need to develop the capacities in Mexico to have people that can process the raw data from radar to end product. So we are going to train people, we are going to develop capacities, and we are going to develop data processing facilities in order to generate these end products.
Thank you.
Regarding this international cooperation, are there already MOUs or what kind of conversations are going on? Could you talk specifically about disaster monitoring and remote sensing?
Yes, we have MOUs with several space agencies. We are discussing MOUs with Brazil and Argentina in our region, and Dr. Mendieta is leading this kind of effort to try to put the ALAS, the Alliance of Space Agencies in Latin America, and as a part of this is a continuous work, because already there has been identified disaster data related sharing as a key factor that could help us to solve this global challenge, and the other is capacity building. So the idea is to try to establish, there are going to be a next meeting in the coming months, and from that meeting we expected to have a clear vision of what MOUs or legal documents will be necessary to start to deal actively with the sharing of information between our countries. Well, thank you so much.
So at this time, I would like to introduce myself because I have the next presentation.
You need the sound?
No, it's okay. Okay, my name is Freddy Pranajaya. Thank you for the opportunity to present. I'm from the University of Toronto, and this morning I would like to present what we call the microspace mission, which is basically a summary of missions that we have done in our laboratory in Toronto. We are part of the University of Toronto, and we develop missions across for partners across the globe. At present, we have 11 operational satellites, and our mandate is actually to challenge the present state of the art for satellite systems. And I will show you some examples after this. And I understand that we are a bit short in time, so I'll try to go through my slides rather quickly. But we have developed some of, we believe, and some of the most advanced nanosatellites and microsatellites that's operational right now. And this is also supported by a new center that we have, the MSTC, which is our home in Toronto. These are the 11 satellites that we have operational, and I'll just, I think I'll just glance through this one because I will go through the individual satellites in the later slides. And all of these are operational, the oldest one being MOST, which was launched in 2003. This is a list. The list that's highlighted in blue are the ones that are presently operational, and we have the remainder of the mission below that is under various stages of construction or just waiting for launch. And because we launch as a secondary, we are subject to the schedule of the primary spacecraft itself, and therefore in some cases there is some delay, so we have to wait, and the satellites are simply waiting in our clean room. I think I can skip that. This is simply the different type of buses that we've built. So we've built anywhere from a triple CubeSat all the way into capability up to 150 kilogram, all using the same architecture, the same electronics. So we're not forcing anyone to, you have this, you have to buy a 50 kilogram bus, or you have that, you have to buy a 200 kilogram bus. We say, well, what do you need? And then we'll wrap our system around your requirements or around the requirements of the mission itself. Some pretty pictures of our satellites. Again, in the interest of time, I'll just go through this rather quickly. There are more in details later on. This is one of one of the first of our next generation small microsatellite, large nanosatellite, which we are building for the Indian Space Research Organization. It is a satellite capable of multi-angle observation in 3-band in dual polarization for studying aerosol distribution over the Indian subcontinent. At present, it is actually in the AINT stage, assembly, integration, and testing stage, and we expect to have it ready for launch next year. The overall bus is about 15 kilogram, with the main bus measuring 20 by 20 by 40 centimeters, and with the addition of the main fixed wing for the generation of additional power. And SFL design everything. We hold the IP on all of the computer systems, electronics, radio system, and so on. And we also design the instrument with input from ISRO, of course. This one is quite a similar bus, as you can see, same mass, similar in size. However, because the operation does not require significant amount of power, we do away with the wings. So just simply the main bus itself. This one is actually being built for a company in Montreal, Canada, in Quebec. for the purpose of monitoring greenhouse emissions from different potential target sites. We expect this to be ready next year as well. This is the fourth satellite that we are building for Norway. I'll go through the other three after this. And this is, again, it's having quite a similar shape, but it's actually carrying three different payloads. AIS is obviously one of the most important things for Norway, given the vast majority of ocean that they have to keep under surveillance. But there's the one interesting thing is, well, obviously there's the Langmuir probe, but one interesting thing is the solar irradiance measurement. Our understanding is that it's actually based on a payload that was flown on it's not Clara. It's Clara is the name of the instrument, but it's SOHO. It was based on an instrument that was flown on SOHO. So it's actually we are using nanosatellite to try to produce a big mission level science data. So again, it just goes to illustrate that you don't have to go very big to achieve good data, and I do actually have some science data to support that in later slides. In addition to the small satellites, the nanosatellites, we are also supporting microsatellites development and activities in Canada. MOSE is the first one, as I mentioned, was launched and is presently still operational 14 years later. M3MSAT was supposed to launch back in July on a Soyuz frigate, but the decision was taken by the government to postpone that launch until next year, even though the spacecraft is completely ready. And we are also developing a high-resolution satellite for Slovenia, 72 kilogram, with an instrument that we designed to achieve 2.8 meter with a pan sharpening from the primary instrument, observing in the 4 bands, having that kind of a swath width capability. In addition to that, the satellite also carries a secondary instrument with a much coarser sampling distance of 40 meters and quite a large swath. And the pictures on your right actually shows the spacecraft under integration for testing. That's actually the flight system being tested in our laboratory. There are some interests, as I understand, about maritime vessel monitoring, so I dedicate the next few slides on that. We are quite experienced in integrating the maritime surveillance satellites, with 3 in operations and 4 more under construction or ready to launch. Just some of the pictures of the launch that we did previously on our 3 satellites. It's 2 on PSLV and 1 on Soyuz frigate. The first one is NTS. This is quite notable in that we built this from contract signing until delivery in space. It's 7 months. We also ended up performing a modification to the launch vehicle to accommodate this satellite at the quite last stage of integration. But it is supposed to only live for about 7 weeks because the sole purpose of it is to demonstrate a technology, so it doesn't need to live very long. But it's actually still operational today and still being used to generate data 6 years later. And we operate that from 3 separate stations, 1 in Toronto and 2 stations in Norway. And the thing that we were able to learn from this mission were actually used for the development of the M3MSAT microsatellites. Some data, some of the pictures that we have during integration from breadboard level system tests into the integration of the satellite itself, satellite ready in the clean room, and finally ready for launch, and on the top collective accumulation of the data over a few months, I believe. Then come ASAT-1. This is the first one that we built for Norway. Norway has a unique challenge of needing to keep track of all of the Norwegian waters, not only for the sole purpose of maintaining sovereignty, but also in the event of an emergency. If there is a cruise ship or a cargo ship having problems in the north, they need to know where it is so they can dispatch the proper rescue systems. And it's actually quite difficult to observe all of those waters with aircraft. Aircraft are very expensive, has a limited loitering time, and has a very limited coverage. But with a spacecraft, you get an update basically every 90 minutes, 90 to 100 minutes, depending on your orbit. So this is the first one that we did, and everything was working perfectly. 4 years later, it was declared a complete success last year, and we are able to achieve a 90% availability. So it is actually intentional because we are keeping, the Norwegian wants to keep the operator's costs as low as possible. So the 97% actually comes from, for example, you have a long weekend, you have no operator, and the satellite needs servicing. But because there is no people on the ground station, then the satellite has to wait until Monday. So Monday comes, the operator commands the satellite, and satellite comes back online again, and that's how we get the 97%. So it actually, the data is being used while the primary user is the Norwegian Coastal Administration. Data was actually also used by NATO and over their operations over the Horn of Africa, and also when during the instance of the Japanese earthquake in 2011. The other interesting thing about this is that it started as a demonstration, but as soon as we obtained the first data, within 24 hours on the top picture right there, the Norwegian decided to make this satellite operational. So we are actually, well, it is actually being tasked as a normal operational mission. And they realized, the Norwegians realized the importance of this mission, of the ability to cover their territorial waters, and they actually then decided to order the second one from us, and it was launched last July on Soyuz Fregat, and with that we expect to have a much improved availability, observational availability, even with no change whatsoever in the operator's operations cost. And then there's a third one as well, and the third one, it was supposed to be a copy, except that they have decided to fly the next generation AIS receiver. And this is almost ready to fly. We are doing some final tests, and we expect to launch it next year. This is a similarly sized spacecraft, but we are building this for Exact Earth, which is a company in Canada. One main difference is that the antenna is actually deployable, because this is required due to the restriction on the launch vehicle envelope. Now, okay, so that's the end of the maritime discussion, but we also do missions for scientific purposes. This is Bright. It is supposed to be a multinational constellation. So we believe we actually have two operational constellation, nanosatellite constellations right now. The first one being the AIS satellite, and the second one being this, because at this point in time we have 5 satellites fully operational in orbit at different polar orbits. And we are able to achieve a 12 arcsecond pointing stability, which is required. I'll go back into that later on. But this is to illustrate where we are. There's a discussion from our colleague from ITU yesterday about having multiple stations across the globe. We actually have several stations across Canada, and over Europe, Slovenia, and we're deploying a station also in India. But for this particular one, we have 3 stations: Toronto, Graz, and Warsaw. With the first 2 Austrian satellites being launched on PSLV into Dundas orbit, and then we have the first Bright Poland from the Bright satellite from Poland launched on the Dnieper, followed by Bright Canada, also from the Dnieper, and then finally with the second Bright Poland, which was launched by Long March in August. So we have this constellation right now operated through the 3 different stations. There's some benefit actually to that, in addition to being able to download more data, because we have 3 stations. But if some station has experiencing some problems with interference or something like that, then we can actually solicit the help from the other station to complete the task. And all of that are being arranged through ITU, so I think we are kosher. In terms of the pointing, I mentioned a little bit about the platform being able to achieve 12 arc seconds. This is actually some data to show that. The RMS error is actually 11.8 arc seconds. And over the long term, we are over a 6-month campaign. Our pointing stability is actually meeting the requirements with quite a big of margin. Some data that the scientist was able to see, and they're actually looking for that dip that shows the brightness variation of the star itself, so they can then proceed to start to perform their analysis. Similarly speaking, with additional observation. And then the next one that we have is these are the 2 formation flying satellites, which was launched from PSLV also last summer. The 2 was actually ejected away from each other, and once we complete commissioning, we ask one of the satellites to fire its thruster to chase the other one, and then once that's completed over a period of 6 weeks, it enters into formation flying, and we have achieved 1 kilometer and 500 meter along track formation with sub-meter control and centimeter level determination capability, and all in 2 satellites, each weighing 6.5 kilograms of that size. And we are continuing to do a closer approach and then doing a different kind of formations, and we tend to illustrate that it is actually indeed possible to do an autonomous formation flying with very small nano satellites. Autonomous because all we have to do on the ground is just press enter, and then the satellite takes care of all of its algorithm and operations. With a lot of discussion going on with orbital debris, we are actually developing a satellite technology that will help with that problem, that we hope that will help with that problem, and this will be tested in 2015 once it's completed. That is actually a prototype of the drag sail, one of the drag sail that we have built in-house. A brief summary of our center. Perhaps the picture actually speaks better than the words itself. This is our home in Toronto. If you had a chance to be in Toronto, then please feel free to contact us. And then if you would like to have a visit. In addition to that, we also in the same building we have our station here. This is when there is a pass, when it's actively manned by operators. But usually all of our passes has nobody in there because the satellite takes care of everything on its own. So when you come unannounced and then we have no operators, then all of the screens are blank, no excitement, but rest assured, satellite is doing fine, collecting data, downloading everything automatically, and then distributing the data to the concerned parties. So a summary of our capabilities. You can read this, I guess, on the PDF that will be handed out later on. The other thing is that we also realize that now that a lot of people can build their own satellites, launch, however, it's a completely separate activity. So in support of our own mission, we do procure our own launch. We do not go through brokers. We speak directly with the launch vehicle. In some cases, we tweak the structure of the LV to fit our requirements, our missions, and we have been able to do that with Rocket. We flew on Cosmos 3M several times on PSLV, a couple of times on the Nepper, and we are working. We just finished our first launch with Soyuz Fregat, and we are looking forward to have more, obviously, with our collaboration with Roscosmos. Whenever we have a launch, we obviously invite all of our partners to share the launch with us, and so to realize cost savings for everyone. We have actually access to different launch vehicle, including the heavy ones, the Zenith, Proton, and so on. We have access to exotic orbits, rare orbits, Dundas orbits, and so on. L2 magnetosynchronic re-entry orbits. We can, if we want it, we can get those. And we have been offered space on those flights. And we, as I mentioned, we speak directly with the launch agency. We don't go through anybody. So in many cases, we actually establish a direct MOU, direct communication between SFL, our lab, and either Roscosmos or ISRO or Norwegian Space Center and so on. So I think, yes, this is quite important picture because we actually have a little photos on the fairing of the Soyuz as it goes up. This is actually the launch of ASAT-2. So the conclusion, you can read this also in the PDF because Werner has been flagging me for time. And I think at this point in time, I can take maybe a couple of questions, but I will be here today and tonight, so feel free to come up and ask me additional questions if you wish. Thank you very much. So, if maybe a couple of questions, yes. Sorry? Okay. All right then. Thank you very much. We will have a 5 minutes break before the start of the next session. Okay, for the presenters from session 7, we have been asked to come up to the stage so we can have a memorabilia taken. Sorry, but I have to go through it.
No, yeah, no problem.
We should have a discussion.
Yeah, of course. Juan, la foto. Bueno, no tú, sino tú arriba. O sea, ¿quién más fue? Fernando Aguado fue. Fernando, Juan, Matt Daniels, Matt.
He might have stepped out. Yeah, I didn't see him.
Getting used to it, but now I have to go back.
¿Ya se fue? Ah.
Today night. Yeah.
Okay.
Yeah.
Que suban tantito a la pantalla, ¿no?
Is there somebody, 2 others, right?
Yeah, Matt Daniels is not here,
Yeah.
so I think that there is.
And there were 2 more from UNAM?
Oh, yeah, Saúl.
Saúl y Saúl, ¿no? Los dos Saúles.
¿Salió?
Ah, de la... ya.
Todos aquí tenéis acento habitualmente
gringo, ¿no?
Sí, gringo.
So
si quieres, vente de este lado para ponerlos juntos. ¿Cuánto tiempo llevas?
Lleva 12 años. Bueno, en ese 6.
Thank you.
¿Tú vas a presentar a los dos, no?
Bueno, sí. Bueno, sí, bueno, sí. ¿Escucho bajo? Sí, bueno, sí. 1, 2, 1, 2. 1, 2, 3, ¿sí?
Sandra.
Ladies and gentlemen, we continue with the session 8. Good day, ladies and gentlemen. The first session is with Mr. Mod Izzet bin Mustafa of Malaysia. Please. Mr. Mustafa is employed from October 2004 to 2008 in astronautic technology, SDN BHD Saham Alam, Malaysia. He's engineer of propulsion since October 2008 to 2012 in astronautic technology, Samahala, Malaysia. He's senior engineer of propulsion mechanical engineer since January 2012 to present in astronautic technology, Shah Alam, Malaysia. Please. Es muy largo el de Turquía. El de Turquía no lo puedo subir. An announcement, please. All the feedback forms, please you leave in the desk before the lunch.
All right. Thank you, Mr. Chairman. Good morning, everybody. Thank you for having me here. First of all, I would like to congratulate the organizer of this well-managed symposium, UNESA, CICESE, and also the Mexican Space Agency. So my presentation basically divided into two main sections. The first section is a little bit about my company and its experience in developing CubeSats. And the second session is about the development of a 3U standard bus satellite, and what we call 3U. So a little bit on my company. My company is Astronautic Technology Sdn Bhd, or ATSB for short, and was created in 1997 under the Minister of Finance Incorporated Company. And the creation of the company is to establish with the mandate of implementing and commercializing space technology development in Malaysia. So in 1997, the Malaysian Space Agency have not yet been established, and the ATSB was established first in order to execute space industry in Malaysia, and the Malaysian Space Agency was established in year 2000. And the first activities by ATSB is the development of Tiongsaat-1. It's a remote sensing satellite. This is a technology transfer program between ATSB and SSTL. The next was Razasat satellite, a medium resolution remote sensing satellite. This Razasat was launched in the year 2009 using Falcon 1 of SpaceX. So a little bit on the experience that we have within the company. The company have gained experience and technologies from small satellite development program, namely Tiongsaat with STL, Razasat with Cetra of Korea, and also through our internal in-house development program, which we call CubeSat and InnoSat. We have more than 10 years experience in launch campaign as well as the management execution of the launch activities. So these are a few pictures that I have taken out to show you the development of, this is during the development of Tiongsaat-1 with SSTL. And this is the bus structure main chassis for Razasat, and this is the camera for the Razasat. So this is the joint development with Cetra of Korea. So throughout the years, we have acquired a few technologies. For example, in manufacturing of solar panels. So we have experience in manufacturing mini satellite solar panels for our own use and also CubeSat. Among facilities in ATSB, we have two classes of clean room, 100K and 10K. 100K clean room mainly are used for AIT activities. We have an overhead crane that can basically accommodate around 200 kilograms of mini satellites. Inside the class 10K laboratories, mainly for optical alignment activities, we have about 12 meters of optical table with air damping system. And we also have solar for large area pulse solar simulator. So these solar simulators are used to basically measure the electrical performance of our solar panels. The solar simulator can generate equivalent of spectral density of the sun at AMS 0. Others equipments, for example, thermocyclic chamber, universal test machines, and also PCB prototyping machines. So in ATSB, we have experience in developing in 2009 two CubeSats. One what we call just CubeSat, and the other one is InnoSat. So the difference between these two satellites is CubeSat is basically an in-house development of our engineers. We develop the bus and also the payload, whereas for the InnoSat, we develop the bus and the payload is basically provided by a few local Malaysian universities. So in CubeSat program, this is way back in 2009. It's a combination of COTS components and our in-house development. For COTS, I think we purchase mainly the solar panels, the power distribution modules, the OBCs and the structure, and for example, the ADCS telecommunications, we did it in-house. And this particular CubeSat, the payload is a cool gas micropropulsion system. As you can see right in the middle here, this is the propulsion system. It utilizes compressed nitrogen gas to basically to produce thrust. And at this time, it's only controlling one axis, which is the longitudinal. And the nozzle for this propulsion system using MEMS technology, whereby we photo etch silicons into nozzle profile, which basically when the compressed nitrogen gas funneled through this nozzle will create thrust. We also developed a CMOS cam for this particular CubeSat. And as I informed previously, there's another CubeSat that we basically developed is InnoSat. So the bus of the satellites are basically the same as the CubeSat, but only the payloads differ. So the payload basically provided by several local Malaysian universities. And this is the first experience that we have in basically organizing external payload customers that will use more or less a generic bus from our side. So during this program, we basically go through a complete cycle with these universities in terms of developing satellites, meaning all the milestone reviews and all the qualification and acceptance tests. So this is just a picture of the InnoSat program. So a similar bus, more or less, but a few boards from the universities. For this basically project, the universities, I think, develop an attitude control algorithms and also some cosine sensor. At ATSB, we have also a ground station to receive telemetry and to give telecommands to these CubeSats. So we set up a small ground station at the top of our office building, and we have the usual equipment, antenna system, control, tracking. And both of these CubeSat and InnoSat actually have gone right until acceptance test. And this is some pictures that I obtained during the AIT at Cal Poly USA. So as I was mentioned, that the project of RazaSat, which is the medium resolution cameras remote sensing satellite, were launched with Falcon 1 of SpaceX. And we are the main customer of SpaceX at the time, and there is available volumes inside the Falcon 1, and we decided to utilize by launching this CubeSat and InnoSat together with RazaSat. So in order to basically integrate both of the deployer inside the Falcon 1 fairing, we developed what we call a secondary payload adapter and separation system, SPAS. So the SPAS is this structure right above the conical adapter. So the main payload, which is RazaSat, will mount it on this SPAS, and SPAS will mount it on this conical adapter, and all the CubeSats within the deployer will be mounted on SPAS. But unfortunately, a few months approaching to the launch date, SpaceX discovered that the vibration levels of Falcon 1s exceed and they have to basically install a damping system between the conical adapter and the main payload. So because of this, we cannot install SPAS, and the result is both CubeSats did not launch, but only RazaSat were launched in year 2009. So this currently both CubeSats are currently in ATSB waiting for launch opportunities and also funding for refurbishment activities. So that is a little bit about the history, our experience in CubeSats program. And following up with the InnoSat program, we believe that the InnoSat program is a very good platform for Malaysian local universities to have space mission and space activities within their organization. So for this, we basically start a project, what we call a Tigayu, by leveraging the experience gained during development of the two CubeSat in 2009. We have begun a development of a standard or a generic 3U CubeSat satellite bus for operational use. So these development programs, like I said, were initiated as a means to commercially cater growing interest in CubeSat mission by local universities. The main motivation is basically to develop a standard or generic CubeSat satellite bus. And with this 3U bus, payload developers, which is mainly the Malaysian local university, will be able to focus their effort in developing their payload system solely while having an operational satellite bus to be ready to be integrated with. So at the moment, the 3U bus is currently approaching CDR phase. We have manufactured a few prototypes of the subsystem. And as a whole, 3U bus is not fixed. Each subsystem can cater a certain degree of customization, and maybe additional of new technologies and interface can be added. So this is our mission statement and objective. As for now, we basically designed the bus to have a mission orbit of SSO with altitude between 600 and 65 kilometers with 1 year mission lifetime. The design of the payload will be performed based on this orbit. So before we did system design phase of this 3U bus, we did 2 activities. One is market studies, or what is available out there in terms of CubeSat's subsystem, so in terms of performance and what kind of missions CubeSat are regularly used for. And the secondly is we go to most of the local universities in Malaysia, and then just to know, just to introduce our bus, and then to get to know is there any interest in having a space mission. So this, as you know, Malaysia consists of 2 parts, East and West Malaysia. So this is the East Malaysia, East is West Malaysia, sorry. And the universities that we went, almost about 15. And the research area interest, once we presented the 3U CubeSat platform, they are interested in smart materials, new battery materials, space propulsion, remote sensing camera, antenna system, attitude control system, and the orbit mechanism. So currently, there are several MOU have been signed with one of the, several universities with ATSB for collaboration, and they are seeking fund basically to develop a payload and to be launched using our bus system. So this just a CAD model of currently 3U. So this is approaching CDR level. This is basically an overview of the system architecture of 3U. So we have the usual suspect CNDH, ADCS, telecommunication system. This time around, we have a deployment antenna system, power system. And for the external payload, for example, the communication interface, we provided SPI and I2C with several voltage levels. So in all, I can say maybe 90% of 3U is ATSB in-house development effort. Maybe the obvious one is the deployment system antenna. I think we still outsource that particular element. So this is an overview of the structure. The structure concept is attachable facets. So we believe this concept basically can give a degree of customization. For example, let's say if the payload needs some cutouts, we just have to manufacture a cutouts one of the panels and maintain the whole the rest of the structure together. So as you can see, it's a bit close structure. This is basically to give protection in terms of TID, but I think approaching CDR, this will be further optimized. This is basically the configuration inside the 3U platform. And for this configuration, the payload is at the most bottom. And because of the subsystem have a fixed form factor and mass, the location of the payloads depends on the center of CG requirements.
Mr. Mustafa, 1 minute more, please.
1 minute, okay. So in order to certify the center of gravity requirements, let's say if the payload is more than 500 grams, the ideal location is in the middle, and if less, the location of the payload will be in the bottom. So this is the initial setup. At the moment, as I said, all the subsystems currently in the prototype phase. We have the solar panels embedded with magnetokers, ADCS structures. Batteries have been gone through qualification in TVCs. And then OBC, TS, and EPS is on the board design and prototype level. And this is basically some overview of the spec. So you can have a look at the PDF. And in terms of operation mode, we divided into launch and early operation and nominal phase. This is basically the website that we set up just to give an update what is going on with TGIU bus. And I suggest you can go to this link to have more information about TGIU bus. Thank you.
Any question for Mr. Mustafa? Okay, thank you for your presentation. Next is Mr. Dr. Russell Aslam. Dr. Aslam graduated as an aeronautical engineer from the ITU Department of Aeronautical Engineering. He received his MSc degree, your master degree, from the same department in 1985. Then he completed the diploma course from the Von Karman Institute for Fluid Dynamics in Belgium. With a scholarship in 1986, he received his PhD from the same institute. Mr.
Thank you, Mr. Chairman. And I would also like to thank the organizers and UN for the excellent organization and the support before I start my talk. And I'm going to try to give examples of our activities as Turkish UNISEC and the organizations involved within. So I'm coming from Istanbul, and hopefully 2 years later, we'll be meeting in Istanbul. Our university is somewhere here. Well, we are here basically for what's written in this slide, and the small satellites are our main interest, and we see the importance of growing interest towards these kind of satellites. Our efforts actually are part of Turkish space program, and Turkey's involvement with the space sector actively started in 1989 with a number of communication satellites bought, and the first one was in orbit in 1994. And in 2005, there was a space program with defined projects and a good budget. And, well, of course, Turkey needed development of qualified workforce to support the space plan. Here we see a list of spacecraft already in orbit and being developed. We have two parts. Here we have the kind of operational, more expensive spacecraft, and here we have the educational and to be also operational. And Turkey is interested in developing Earth observation satellites, and actually there are two already in orbit developed by Turkish engineers. And now there is a project started also towards development of a communication spacecraft. Of course, all include international cooperation. And here there is the CubeSat roadmap I will also describe. Well, in Turkey, there was one astronautical engineering department, and we have started the CubeSat development. Well, of course, this is as all described during the week, an interdisciplinary effort. And owing to the importance of space technology and applications, now we have many other new departments. And we wanted to share our knowledge and infrastructure with those new departments. And we thought it would be a good way to establish a union with all of them towards that goal. Well, of course, we got the idea from Japan, the UNISEC of Japan, actually. We met first time in 2010 with Professor Nakasuke and Ms. Kawashima. And then seeing the activities happening in Japan, we decided to follow a similar road. And well, during the week it was mentioned, there is the CANSAT Leader Training Program, Mission Idea Contest. And this is actually an international platform, although it is run, or it happens mainly in Japan. And then in 2011, we have also taken the initiative to establish a Turkish UNISEC. But we have not included only the engineering side, also the space side, which is the sensor side, actually, which needs quite a lot of support because they are not in an advanced situation. And again, as history, we started in November 2011 with the management of the rectors of 3 universities in Istanbul, and there were over 20 universities participated and presented their contributions, what may be their contributions towards such a union. And then quickly we got the support of government, industry, and the research institutions, and we had 6 meetings held so far, and 3 of them were hosted by the industry and the government. Now we are working towards making the UNISEC Turkey, we say UTEP, as a legal entity. Now we are going on as a voluntary process. And of course we would like to define a joint project with government and industry and supporting the national needs, and together with international cooperation. We are also the part of UNISEC Global in that respect. For example, here we see 2 of the meetings. We sometimes try to have the meetings in conjunction with the national or international meetings held in Turkey. This is a good way to gather people because they are already there. And this was supported, this meeting was organized by the National Research Council, and they managed all the related costs, actually. And this is our logo prepared by UNISEC Global. So this is our international logo, and we have also the national logo. The main actor is Istanbul Technical University regarding CubeSat activities. We started in 2005, and now we have 2 spacecraft already in orbit, and now we are also part of the QB50 with 2 spacecraft development. But we have, since the work is interdisciplinary, we made a connection with the industry, and particularly we are an astronautical engineering department, so we have to work with the mechanical, electric, electronics, sometimes industrial design, telecommunications. So now we have a very big group, and we get together as required. Of course, we have also established the Amateur Satellite Society of Turkey. The radio amateur community is very important to CubeSat and spacecraft development. And we have spin-off SMEs, micro SMEs. They are also important. Here we see a list of partners. These are student companies. Turkey provides startup money in the order of $60,000 for successful young graduates. And in our labs, we employ the undergraduates, and when they are enough skilled, they are employed by these SMEs. Well, we are interested in usually small-scale satellites, but we also provide support to the national big-scale satellites. And together with some partners that are already here, we have submitted 2 Horizon 2020 proposals, and this was just short. hope to get funding next time. Of course, we have, before developing spacecraft, we have quite an experience in developing aircraft, and we had the infrastructure. This also was very helpful in developing capability towards spacecraft. Here, well, I present this usually when I have 1-2 minutes. This is almost all the capabilities we have, but I will come to that very quickly. One thing, when we started the CubeSat development, we did not have any AIT in Turkey. Now we have very good AIT centers. So therefore, we had to establish everything in the university for CubeSat or spacecraft component testing. Therefore, we have a clean room, we have a thermal vacuum chamber, we have shake table, we have EMC. Some equipment was procured part of some other national projects, but now we are also using them mainly for space testing. We have also an VHF, UHF ground station with automatic tracking capability, and we can, of course, cooperate in that issue. In this chart, I tried to, if you can read, the development from the simplest project, which is ITU-PSAT-1. It was launched in 2009. It's in orbit, and the beacon is still operational. Many times it is used by the new ground stations or radio amateurs as a check of their ground station. Now I will talk about the other projects on the pictures. So the ITU-PSAT-1, I think it was kind of similar to what Tokyo University sent in some 6-7 years ago. And, for example, the communication, both-way communication was using the same frequency, and this was a problem. Then we, following the ITU-PSAT-1, we proposed a project to the Turksat, and they funded the project, fully funded actually, but they asked all the systems to be redundant. Well, then we had problem. You see, it's a very complicated spacecraft because you have a main system and a secondary system, and sometimes it was hard to place the solar panels because of the amount of cables. Here we learned something, and you should prepare your spacecraft software before your spacecraft is ready. Here we were able to test in orbit the linear transponder for voice communication. We follow the usual spacecraft development. We have the satellite, test integration, and ground station. We also have all the equipment. We start with the design, desktop model, engineering, and flight model. We do all the major tests on the engineering model. Here you see this is a EPS system with supercapacitors, and this is another system being tested in the thermal vacuum chamber in our clean room. Here the two engineers working for integration of the 3USAT, and these are electric, electronic, astronautical, and mechanical engineers. This is complete, and another, well, difficulty, another problem, but we had one antenna for each system, then summing up to 10. Here, the EMC compatibility test in the electronics faculty. And it was launched from China. You see the engineering and flight model together. And it is very exciting to be part of launch campaign. I was there 3 times. Usually it is very tiring, but because it takes too long to go to the launch sites, but still very exciting, and it's fun, actually. Then, with this experience, we were easily accepted to the QB50 project. Now we are providing two-unit spacecraft, and we have completed the CDR and accepted fully. As you see, in the QB50, there is a science sensor. We are using multi-needle Langmuir probe to make atmospheric measurements from 380 to 90 kilometers. And we have also developing an X-ray detector and to lay the ground for scientific sensor development in Turkey. Well, the importance of QB50 is the CubeSats are the main passenger to the orbit, not secondary. That's the importance. Well, of course, it has education, scientific, and in-orbit demonstrations elements as well.
Mr. Aslan, 1 minute.
Yes, I'm completing.
Perfect.
And this is the X-ray detector. And we have finished all the tests of the X-ray detector. It has its own batteries, so it is not consuming from the main system. This is the system diagram with all the elements. So what is good about QB50? It's a good example of multi-institutional international collaboration and cooperation. There is mix of budgets. You get from QB50 kind of in-kind and the local budget. The local budget comes from the UTEP members, aerospace industry, and I2 spin-off. Usually industry, if it is starting in the space activity, if it is a new company, they are ready to support CubeSat efforts. And it's a very good school for enhancing spacecraft design, management, and ground station operation skills, because the documentation is very important and it's really nicely prepared. This is the calendar. Launch is foreseen for early 2000, but it may be delayed a little bit. We have a ex-UK bond project with the industry again. You heard about the UNICEF Global. Recently, we have given a 2-week CANSAT Leader Training Program course, and majority of the students, well, they were professors, but space science, and they never had any interaction with spacecraft. Actually, in 2 weeks, here you see, they learned how to develop, and this was the developed CANSAT, and it was launched by a rocket prepared by our students, and here you see the CANSAT and the rocket deployed nicely. We have also outreach activities. We go to many places, including elementary, high schools, and public places. And here you see a CubeSat, and this is printed by 3D printer. We have also given international courses like thermal vacuum chamber education. So I think I can conclude here. Thank you.
Any question for Mr. Aslan? Okay, thank you for your presentation. The next speaker is Mr. Mauricio Ramiro Enriquez Scott from Chile. The Professor Enriquez currently works at the Austral University of Chile. He has a master's degree in science from the Complutense University of Spain with a specialization in robotic and space technologies. He is currently in charge of the first Chilean moon rover. The project has the support of the Chilean government, and it is a joint endeavor between many Chilean and foreign institutions and universities. The rover design and specs were shown at the NASA and presented at the Space Tech Expo in California, USA of last year, as well as the last two FIDE events, the biggest international air and space fair in Latin America. In all events where it was presented, he caused great interest and praise. Please, Professor.
Hi, can you hear me? Okay, I know that we are all very tired, so I promise it's not going to take more than 1 hour, 1 hour and a half plus questions. Okay, let me see if this is working. Okay, well, my name is Mauricio, and I want to start thanking all the organizers, especially UN and CICESE, for great accommodation, great food, too many drinks, and great new friends, so thanks to all. Well, I think that often we, especially in Latin America, we feel like this from time to time, especially the second picture where an energy drink seems to have a better space program than our nation, and that's true for Chile too. So I want to talk a little about the background in space for Chile. Chile has a humble space development, but it's a old space development. From the 1950s, NASA built a tracking station in Chile, and we helped with a number of Apollo missions, and even with Soyuz mission, also with shuttle missions. Right now, it's below to SSC Chile, which is a Swedish company, but universities can access this tracking station under an agreement. The satellite experience in Chile is also very humble, but back in 1995 and 98, we tried to send two microsatellites. Actually, just one of the two satellites actually works. That's the Chilean way to do things. We like to do things twice. It's more fun to do just do the right thing at once. So Facade Alpha fails to separate from the main structure, and Facade Bravo was the successful one. In 1999, there was a really great experience for a group of schoolgirls that developed an experiment that was sent on the Columbia shuttle for the STS-93 mission. It was a biological study for play control. It was a great experience for those kids and for the country too. The current satellite that Chile have working is the Facade Charlie. As you can see, we are not too clever to name our satellite, so everyone can bet which is going to be the name for the fourth one. It's a little bigger satellite, it's 130 kilograms, and it's mainly for observatory experimentation. The Air Force also built a ground station for tracking the satellite and control the satellite. So that infrastructure is also available for universities in Chile. Of course, in Chile we have a great infrastructure in terms of astronomical observatories. That's a great example of international collaboration. Chile, as you know, have a great sky at the desert at the north of Chile. So most of the biggest astronomical observatories here in Earth are located at the Atacama Desert. Two examples are the ALMA project and the BLT. Some current development on the satellite and rocketry area there are some universities working on in Chile are the SUCHE, which is an endeavor of the University of Chile for a CubeSat, which I know that is ready, and I think they are looking for launching opportunities. And the University of Concepcion, which I think is the only university in Latin America that have the aerospace engineering career, have the sounding rocket project for atmospheric experimentation, and also a solid engine project that can be used for a TLI, for a translunar injection, as also as a lunar brake engine. But in my university especially, we are working in a CubeSat mobile exploration platform. We are trying to improve the CubeSat capabilities in two terms. First, to allow CubeSat hardware to go into deep space, and the second one to allow to CubeSat form factor vehicle to move into a surface, especially a hard surface. So this is a render of the rover that we are developing. We started working as part of the GLX Prize competition a couple of years ago, and now our university is in charge of the development of that rover, in conjunction with a number of partners that I am going to show in a little moment. But we are also present this rover development in many different events in Chile and also outside. This is our current constellation of stars. That's what we call it. Is all our partners, local and international partners, that are working with us in this development. For us, it's a key factor to have those international partners helping us in this development. We have some support from NASA that are kind to send moon imagery, moon simulant, and other information and data. We work with the University of Berkeley and also with the Auburn University and a number of companies in Chile and also universities in our country. The main idea to develop a robotic rover as a payload is to develop those three key things. First of all, to have a payload to send somewhere. We usually talk about to send it to the moon, but we are also discussing the possibilities to send it to the Mars or even an asteroid. The second thing is to start the rocketry development in Chile. Not necessarily to launch this payload, but as a second option. One of our main options is to pay for an orbital ticket and go from there. And the third part of this endeavor is to create a national and international partnership to create build capabilities in Chile for many satellite component, rocketry component, as also potential rover components. The main goal of this endeavor is to have a cultural change in Chile, as also to create a Chilean space industry. Our rover is a bio-inspired design. We make a deep study of the insect legs and how they move. So we create something that is a minimalistic rover. That's the honest way to do it, because in Chile we can't think in a big rover like Curiosity or something like that. We need to keep it realistic, so we create the smallest and minimalistic rover that we can think of. The design allows us to have several potential. From it can be scalable, we can work in many different sizes. It can tip over, so we can recover it from if fallouts or something like that. And it can fit inside a CubeSat. As I say, it's very minimalistic. So I want to show a video, if it's possible, the number 3A or 3A or 3B. Just to show the main idea. 3A, yeah. That's an old animation. Actually, do not represent the actual state of the mechanical. It's just an animation to demonstrate the idea. It doesn't represent the actual state of development of the mechanical system. When the rover is inside the CubeSat, it takes that shape, the previous shape, which is a sphere form, and when the rover is out of the cube, it takes the exploration mode or open mode. But to do that, we are working with an international company that works with nitinol, which is a bendable, intelligent metal alloy. That puedes mostrar I'm going to show the second video, the 3C. That one is an actual simulation of the nitinol. In that one, I think we were using the superelasticity property of the nitinol for the bending of the wheels. We are exploring the two main properties of nitinol, the heat shape memory and the superelasticity. This one is using superelasticity, I think. Okay, you can go back to the presentation. the previous one. That one. In our development, we develop many different versions of the rover, from the micro dandelion, that's the name that we use for our rover, which is an educational outreach for our development. We work with many college and basic and high school college, and we work and build these little robots that use a solar panel to move. The mini dandelion is the one that fit inside a CubeSat, and we also have some other bigger prototypes where we test some other component and areas. We have many different build stage for all those rovers. We have most of the engineering analysis for the rovers. We have engineering components also for some of the prototypes, and our universities are working to build, to create build capacity in our laboratories for clean areas, vacuum chambers, vibration tables, and all that. We have the luck in Chile to have the Atacama Desert, which is a really alien surface and area. So we can use those facilities that are in charge of the Atacama University for our rover test. I want to show a video, the number one, which I think you are going to enjoy. That sound is not part of the rover. Just 15 minutes or something like that, don't worry. We can see it again later. No. You can go back to the presentation, please. Okay, here are some of the characteristics or specification of our rover. I'm going to try to be more quick to leave more room for specific questions, and if you want, in case you want to see the video again, no. Okay, but I do not come here to say that everything is great and we are working perfectly fine and everything is dandy. No, we have a lot of problems, of course, like everyone else in Latin America. First of all is the money, of course, but for Chile at least, it's not the direct problem. In Chile is in a very good economic situation right now. We actually spend more money in reality TV shows or selling and buying football, soccer players and stuff like that, and doing things twice, like the satellites instead and doing just once, right? So the money is an indirect problem, actually. Our biggest problem is that the people that are in charge of the decision making doesn't have the necessary technical knowledge or the seriousness to keep this kind of endeavor forward. On the technical aspect, we need to work in the final flight model of all the components, all the tests needed to have the final payload or rover ready, of course. There are also interesting for some of the university in Chile to develop a CubeSat lander system, which will be another challenge, of course. As also to improve the ground station for tracking this kind of mission. there is a number of institutions in Chile, especially private companies that are working in an alliance to share a financial lunar Mars or asteroid mission, which can be part of a secondary or third payload of a lander that can be developed as part of the GLX prize competition. There are actually there are three teams that are serious enough to offer payload opportunity in their landers. One is Astrobotic, Moon Express, and the team from Spain also. Well, we have the wheel, which is, I think, our biggest potential. So everyone that is interested in enjoying this great adventure can contact us. We are asking for help to anyone that can anything, and we are also willing to help to anyone that think that what we are doing is interesting. So Nicaragua, where are you? Nicaragua. Okay, just have to write me. Okay, so if you think that's something interesting for your country, please do it. So is that if I have see further is by standing on the shoulder of giants. We have the opportunity to inspire the next generation. We have and we must provide those shoulders for our next generation of scientists and engineers. So please join us. Let's go together to the moon. Thank you.
Thank you, Professor Enriquez, for your presentation. You have any question for the professor?
No question. No, great.
No perfect. Thank you so
Thank you very much,
Professor. The next speaker is Mr. Dr. Mohamed El-Kosi. Dr. El-Kosi, Deputy Director of the Egyptian Space Program project, worked in EgyptSat-1 and EgyptSat-2 satellite projects, and now is managing the work in MISR-Sat-2 project and the Egyptian satellite experimental satellite. Doctor?
Here next. Okay. Thank you, Mr. Chairman, and I would like to thank the organizers for being here, and I will try to let you be acquainted with the Egyptian space program activities in this short time. I will address three topics. First, I will show our main activities. Then I will proceed to our current assets, and then I will speak about the prospects for international cooperation. So I told him what happened. Okay, so and then for this one, I ask him to listen. You see? Okay, I will press it. Okay, no problem. Egyptian Space Program was founded in 2000. This program is managed by National Authority for Remote Sensing and Space Science in Egypt, which is belonging to the Ministry of Scientific Research. Now I will start our main activities. The first activity was launching of EgyptSat-1 in 2007. By the way, after I listened to the talk from Mrs. Misa from Colombia, I found that both Egypt and Colombia launched their first satellite in the same day using the same launcher, the neighbor in Baikonur in Kazakhstan. The EgyptSat-1 satellite is a remote sensing satellite for Earth observation with a resolution of 7.8 meter in optical band and 39 meters in multispectral and infrared. Lifetime was 5 years, and now it is not in operation. That project was conducted in a remote sensing satellite with resolution 1 meter. It will, with lifetime 11 years. This project was done in cooperation with Russia. Third action is we are now building a small satellite assembly, integration, and testing center with an area of about 4,000 square meters. This center will include all conventional testing and testing for small satellites, thermal vacuum chamber, mass alignment, shaker, EMC. This project is scheduled to be in operation by October 2017. Fourth major action, which we are doing now, is we started a project to develop an experimental satellite for remote sensing application. We just started last month. We are targeting 15 meter resolution. This is the main characteristics of the satellite. You can see it in the PDF file. This will be also a joint project. The partner is not yet defined, but what we defined is the mechanism of the cooperation. This mechanism depends on buying the subsystems from the partner. Then we will take care of assembly, integration, and testing in our facilities. The partner will share in the consultation, will share in the review boards, and also will be responsible for coordinating the launching. If we review this mechanism, we find that it is exactly comply with the level 2 model, which was presented 1 day ago by Tom from PST in his excellent talk. So I didn't know about this level 2 mechanism or level 2 model, but I find that this model is exactly satisfies our needs. Then I will transfer to talk about our current assets. We have the Space City, which is located 50 kilometers in the east of Cairo, with an area of about 400,000 square meters. Now we have in this city, we have a ground station control building. We have ground receiving station building. We have mission control center. We have the utilities. And there are a set of buildings that are planned to be completed by the year 2020. We are negotiating also to host the headquarters of the African Space Agency, which is discussed now. We are negotiating to host this agency in the space city in Egypt. This video showing the space city, showing the existing buildings and the buildings that which are planned to be constructed. We have the engineering model lab of EgyptSat-1 and its testing equipment, which is used now for training. We have the strength mockup and full-scale mockup for EgyptSat-1 also are used for training purposes. We have space payload lab. We have different labs, I say conventional labs for those who are working in space technologies. We have other facilities. The important thing is we have what is called the Concurrent Design Center, which is an excellent tool to be used for examining the effect of change of any parameter in the satellite on other parameters while doing the mission analysis or the design. We have ground receiving station in Aswan, 1,000 kilometers south of Cairo. We have HRPT station in Cairo. And this is the zone coverage of both of them. We have, of course, the manpower. Now we are 216 members. We started 2001 with 70 persons, and we are still enlarging. We have complete data and documents for EgyptSat-1, about maybe more than 4,000 documents, which cover all the stages of the project. We have the image received from EgyptSat-1, which is available for anyone who wants to use. We have image processing center. Now I will shift to international cooperation. National Authority for Remote Sensing and Space Science has many international cooperation programs. These programs may be covered by involvement in projects funded by European Community or cooperation between US and Egypt or other programs. Also, we have signed MOUs with many international entities and agencies. We have good work with African Union, and we are deeply involved in the discussions for establishment and launching of the African Space Agency. Last slide, I will present the opportunities for international cooperation. We are about to start our third satellite, 400 kilograms, MESRSAT-2 project. This satellite will be developed in cooperation with an international partner. This partner will be selected based on international call for bid. This international call for bid will be issued by the end of this year. Second project, as I said before, is experimental satellite. Also, we receive using our data receiving station to receive images from other satellites based on agreements with the owner of the satellite. Also, we are targeting to enforce the cooperation for building and our capacity and increasing the level of our manpower. Thank you.
Thank you very much for Mr. El Kosi. Some questions in this presentation?
Yes.
Presentation. With regards to Space City, is this a project currently being funded?
What
Space City, the Space City project.
Space City?
Space City,
yes,
that you mentioned.
It's funded from our national fund, from the Egyptian government.
And what is the amount of funding? What is the cost of the project? Because it's a...
Okay,
have any...
I will answer. We spent till now for these buildings, which I showed, for the buildings which already constructed. We have 70 and 40, 150. 150 divided by 7. So what is the result? 150 divided by 7. So to be in US dollars. 100, about 25 million US dollars. Till now. And we have a budget for 5 years to complete the other buildings.
Are you considering private investment in that project in Space City?
No.
It's just government?
All are governmental investments.
Thank you very much.
Another question? Okay, thank you very much, Dr. El Kosi. The next speaker is the Dr. Wang Xincheng. Dr. Wang Xincheng is in the faculty member of the School of Aeronautics, Beihai University, China from 2008 until present. His research interests include microsatellite technology, spacecraft, fall detection and diagnosis, and onboard computer system. He is leading a student R&D team on university microsatellite project in Beihai University. During 1898 to 2002, he has studied and worked on the small satellite in the Chinese Academy of Space Technology CAST. In 2003, he worked in its space transportation as an associate research. During 2004 to 2007, he pursued microsatellite projects work in Shenzhen Space Technology Center. Please, Mr. Wang.
Good morning. I give the presentation is building basic space technology capacity based on micro or nano satellite program. The presentation from four sides to introduce these contents. Our Beihai University founded on October 25, 1942. There are 26,000 students and over 1,400 full or associate professors. There are 42 research institutes for interdisciplinary research centers, especially the aeronautics and astronautics. I belong to the spacecraft technology department, and our department research directions include spacecraft structure analysis and optimization, dynamics simulation, active control of vibration, visual simulation, orbit design and analysis, and multidisciplinary optimization and microsatellite design. Our university and micro and nano satellite program purpose is demonstrate, verify new concept and new technology, and give the students hand-on space engineering practice. We will establish the low-cost university microsatellite platform, and we will strengthen international academic exchange and cooperation. The BOA site mission objective include the ADS-B technology experiment in orbit, the corridor mass deployment verification, and the CMOS industry camera test and space edge imaging. We have a cooperation with the EPFL for this space camera. And we also take the new electronic components in orbit test. And this we have a cooperation with the Chinese industry department company. Except the spacecraft, we also need to coordinate with the launcher for pitchback and the communication, the ground station to telecommand and receive the telemetry data. And the launch site in China And the application center, we will in our Beihang campus and EPFL. The BOE site orbit is SSO orbit, and the latitude is 600 kilometers. And launched in China Taiyuan satellite launch site. It will use the S-band for imaging data downlink, and UHF and VHF frequency for telecommand and basic telemetry data downlink. And the launch time expected at the end of 2015. The specification, the satellite mass less than 40 kilograms, and the size is 320 millimeters long and wide, and the height is 650 millimeters. And the power supply, constant power supply, more than 80 watt. This is the satellite configurations. At the end of 2012, we also take part in the QB50. I think both of almost have familiar with this QB50's work, so I do not give exactly introduction. And we have submitted the proposal and get the committees, the technical committees approved. And we also submit the PDR report and CDR report, and the committees also gave the comments, reviews and comments. So at present we are focused on the engineer model phase work. For our BO site 1, it is a 2-unit CubeSat. Its mission, the first mission is take the science unit 1. That means INMS. It is supplied by the QB50 organization. And another is Beidou receiver. It is a Chinese new components, and we have cooperation with the Chinese company, and we will do this experiment. And this is the, our CubeSat configuration. In Beihang, we have international cooperation. We have a long history on the international cooperation. And this year, in November, we will establish the UN Regional Center for Space Science and Technology Education. And we also have a good relationship with the abroad universities and Chinese Aerospace Industry Department. And every year we have hold the Space Technologies International Conference. And in our university, we also have the basic space technology facilities, such as vibration test bed, thermal vacuum chamber, and thermal sink, and infrared heating cage, and radiation element test bed, and so on. So it will support our project team to work. So based on this background, we give the students hand-on education, and this students is organized project team, and the supervisor and the advisor, not only in Beihang but also in Chinese aerospace industry department, give the students direction. So we the project team do a lot of works such as the structure, finite element analysis, vibration test, the power subsystem test, OBDH test, radiation element test, TTNC ground test. Some of the, such as the TTNC ground test, some of these works we have finished in our company, in our campus, and others we use the industry department facilities to this work. And we also established the UHF and VHF ground station in our campus, and all the facilities is works well. And we also have the plan to establish the S-band receiving ground station to receive the imaging data. And this is the thermal simulation and the test we have done. So our student, our programs, student members not include the Chinese students, but also we have the foreigner students. Here is at present our project team members south. We can see that more than half is Chinese students, but there are also about 80% is the foreigner students. Their students is master for master degree, and they also will take part in join the project team and to pursue for the hand-on practice works. And the project team management, well, we can see that these students from is multidisciplinary team members. That means electronics and mechanics, communication, and computers. And still is flexibility, because the students, some of the students need to have the course, some will do the other works. So we must have a high effective organization to organize these students to work together. And we have effective communication tools such as the email, telephone, QQ, WeChat, and Skype to exchange and communication in time. And the core team members take part in all the project cycle. And we have the regular project work meeting normally once a week, and for the urgent, anytime.
Dr. Wang, 1 minute more, please. 1 minute more.
Okay. So, summary, the low-cost university makers on the non-satellite program is excellent on the hand-on practice education to build the basic space technology capacity. The basic ground facilities are important factor to support the program works. The funding, the project schedule, and the team members need to be trade off during all the program cycle. The launching opportunity need to confirm in advance during the flight model phase. That's all. Thank you.
Any question for the Dr. Wang presentation? Nobody? Okay. Thank you, Dr. Wang. The next speaker is Ms. Lilia Edith Aparicio Pico from Colombia. Ms. Aparicio is major in physics, management, project specialist, master of informatics, science technical doctor, titular professor at Distrital University in Electronic Engineering program, master informatics program, and doctoral engineering program in Bogota, Colombia. CubeSat project scientist director, GTEM's director research group, scientist director of FUNTELMED, Scientific Foundation of Telemedicine Development.
Okay, good afternoon. I am a scientific director program at the Distrital University, and I want to talk to you about not about the technical aspect, but about my fantastic experience around our CubeSat projects. CubeSat UD telemedicine and telemetry is a first project in Colombia in order to solve a few health problems. I am an expert in telemedicine in Colombia. I am a director of Association of Telemedicine in Colombia, and I have been interested in solve the problems around telecommunications and informatics solutions in order to make a special service, offer a special service to our population, our people in Colombia. Okay, some words. What has been Colombia's history on space affairs? Some important aspects are, since 1958, Colombia has been a part of United Nations Office of our space affairs. Colombia has signed 2 of the space treaties. From 2002 to 2006, Colombia was secretarial pro tempore of the 4th Space Conference for the America to develop a plan of action of the space file in the benefit of the American region. Since July of 2006, Colombia has been represented by the Colombia Space Commission, and with the approval of Colombia President today, there is a Presidium program. In 2006, the Aeronautical Civil of Colombia invited us to develop a CubeSat special program. This program it was very interesting because we didn't want to develop a satellite and launch, not only. We want to develop an special educational program to develop satellites, and in order to solve a few critical problems around education and health and telemedicine solutions in Colombia. This is the principal reason because we are working with 3 CubeSats projects that we have. Our first CubeSat is at the laboratory now. We have been working around 6 years learning to make satellites. This is one problem, the technical problem and engineering problem. In order to solve this problem, to learn how to make satellites, we developed Colombia 1. Its mission statement was to develop an academic satellite endowed with the specific technical requirements that allow the training of the human resource in science and space technology and the infrastructure establishment that allows to develop telemedicine applications. This is a special mission because at the moment there wasn't a special mission for telemedicine in CubeSats programs around the world. The objectives of our project: to implement a laboratory of picosatellites research for training and development of a space program that is reverted in an academic environment. As a result, we formed 10 master, 1 doctor, and 40 electronic engineers that in this moment have the possibility to work in the development of satellites in Colombia. The second objective was to implement a telemedicine pilot project with space technology for transmission and reception of ECG signals. The other objective to obtain telemetry and data that can be used to prove project success and guarantees future research processes, as Colombia 2 that has a camera receptor for radar, and 3 CubeSat, it corresponds to QB40, excuse me, to QB. Okay. The primary mission of CubeSat Colombia 1 was the telecardiology test bed between Bogotá to Neiva. Neiva is another city in our country where we have another ground station. Secondary mission will lie downlink telemetry and control through the establishment of the ground segment. Okay. This is the content, or this is the mission, this is the architecture of our mission. We take we have an acquisition module with BQ coder, the quantification vector for compressed signal. We have a control system in order to control the errors because the principal result was in Colombia 1 was we modified the AX25 protocol in order to include data of ECG signals. This is the principal object. This is the principal result of one of our master thesis at the Distrital University. This mission consists in to transmit data and in a X25 tram or frame. Minimum success of criteria to deliver CubeSat to the Dorado Airport for launching. Up to now, we have our mass laboratory as CubeSat because probably we will launch in in 2016 or 2017, I don't know, because this is the principal instrument that we are learning with it. To transmit virtual passing information between Neiva to Colombia. Up to now, the solution was proved between Bogotá, Neiva, and between another station ground in Tunja. We have 3 stations, ground stations in Colombia: Bogotá, Neiva, and Tunja. This is the operation concept. It's simple, a communication through the satellites. The principal resource was modified AX25 protocol in order to include data of ECG or electrocardiograms. This is the common organization management chart for our project. The principal result is where the team leader is an teacher at the district university, and each module of the team technical is a teacher at the district university. The 10 master was formed in this project. The 8 are professors or teachers at the district university. Then the other people are students and other teachers. The team is conformed by 8 teachers that guarantees the continuity of our projects. Okay. Some impacts and where is, or what is, where? What is the spectacular experience? In science, technology, and social impacts, we are transferring experience and technology to Army Colombian organization. Last year, we sent our results to Belgica and present in the International Symposium. They invite us to make a QB40 for European networks in order to study in situ the thermosphere. We have problems around financial aspects. Up to now, we will participate in this project of Belgica or the European community with our 2 station ground, one in Tunja and the other in Bogotá. They will operate with the hands-on networks ground stations. Another results, science, technology, and productive sector. There are civil people interested about developing constellation small satellites for business interests. Another result was to go in order to find financial to solve or to solve our problems to financial aspects, because in Colombia we have a big problem because the presidential, vicepresidente in Colombia canceled the principal project, the government project. But we think that there is probably many solutions in order to the universities can continue working and learning to make honor to the lemma, making space technology accessible and affordable. We want to continue work around about or in many aspects around the spatial technology. Another result is we formed university teachers as a team, 10 master, 10 industrial engineers. In this moment, it's very important that the community, Latin American community around the world, help us to find our objectives, because the development of technology is a little problem to solve in order to solve a few and big problems, social and health problems. I appreciate if you write your questions in order to take an excellent intersection information, because I speak a little Spanish, I write English, and I speak Spanish. No, thank you very much.
Any question for this presentation?
Can you help me? Excuse me. Can you help me in the translation in order to understand?
Thank you very much for your presentation. My question is very simple. You mentioned these cubes as for telemedicine applications. How are you going to launch it? Do you have a plan for launching the CubeSat?
Yes. 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 Okay. We have launched the Colombia UNO up to now because this is this is our laboratory. Yes, this is our product. Around we have two versions of control attitude module. We have 4 versions for power system. We have 4 versions for module of communications. And finally, we have our designs. Yes, probably, I said, probably it is possible to launch Colombia UNO in 2016 or 2017. Now, I have a guarantee to launch a QB, but I don't have money for QB. Yes, and it is probably that there are some sponsor give us a financial to launch Colombia 2, because Colombia 2 has a camera and sensor. I don't know, it's probably.
Another question? Okay, thank you.
Thank you very much.
Thank you for the presentation. Okay, this is the last presentation. First, I think that is thank you for all the speakers for this brilliant presentation. And I finished the session 8, so an applause for all the speakers. 2:30 here after the lunch. For all the speakers, please, we take a picture for the session 8. Miss Aparicio.
So, good afternoon, everyone, and welcome to session 9. And session 9 is titled The Way Forward. But actually, what we are going to do in this session is probably a more important aspect of this whole symposium. We're going to discuss some of the elements for drafting the symposium report. And as you know, on the first day when I made the presentation about the objectives of the symposium, I mentioned to you that the UN symposium is also different from other symposiums for a number of reasons. And one of those reasons is that we actually have a United Nations General Assembly report. And you can see here on the picture the title page of how such a UN report looks like. And it's really kind of a lucky thing, you know, that the number of UN General Assembly reports have been largely reduced because they're actually very costly to produce. So they are professionally edited, they are translated by translators into the 6 official UN languages. And I once heard a figure like one page of this report is probably around $20,000 or so. So you can imagine it's not cheap to produce something, but we have such a report. The report should reflect the discussions, observations, and recommendations made by the symposium participants. And it's prepared by the Office for Outer Space Affairs in our role as Secretariat for the Committee on the Peaceful Use of Outer Space. And as I mentioned, it's officially edited and translated. So, you know, when you read such a report, it has kind of a strange language, a kind of a UN administrative language. And, you know, of course, there are a lot of editors checking these reports to make sure that everything is correct, that the country names are spelled correctly, and that we don't cause any diplomatic incidents by writing something wrong. So, you know, lots of people will be looking at this report. So when we discuss this, don't be surprised if some formulations will be slightly different in the final report from the way we present it here. And what happens with this report is that it's submitted to UN member states through the Committee on the Peaceful Use of Outer Space and through the UN General Assembly. But basically, you know, it's up to you to take this report and use this report to your own advantage. And you, of course, have to identify what is the best way to use this report, because as you can imagine, the UN member states, they are concerned with so many questions, and I mean, there's so many reports out there. So if you don't put attention to that report, it will probably not be noticed to the extent you would like to have it. But if you want to see some examples of previous UN reports, I just wanted to mention to you that actually all the UN documents, or let's see the final documents at least, you can retrieve from a special website. It's the documents.un.org website, and you can find everything there, basically, that has been finalized. And you can search by search words, keywords, or you can also just enter the symbol number. So each UN report has a symbol number. And for example, the reports of the Committee on the Peaceful Use of Outer Space, they all start with AC 105, and AC is actually then Committee 105, so the Committee on the Peaceful Use of Outer Space was the 105th committee, but it's a permanent committee, and then you have a running document number. And yeah, most documents, if not all documents on this website, are available in the 6 official UN languages, so you can also read the reports, for example, in Spanish. And I've just listed here the document numbers of the most recent 3 reports on the Basic Space Technology Initiative. So these were the symposiums held in Graz, in Japan, in Nagoya, and in Dubai, in the United Arab Emirates. And you know, you can just plug the document number into documents.un.org and see what has been written in those past reports. And you can also see there about the observations and recommendations. Now, when we draft this report, there are various sources for putting this report together. So on one hand, it's the presentations you have made. So of course, we also have collected all the presentations, and you know, we may go through the presentations and we may see if there are interesting points, interesting aspects that can be included in the report. So when you read the final report, maybe you will discover something that what you have presented in your presentations. We've also taken note of the questions and answers during the sessions. We have notes from the panel discussions, so this will be included. And then, as you have seen, we had here chairpersons and rapporteurs taking notes, and some of them have already sent their report to me, and I'd like to kindly ask the chairpersons and rapporteurs also to send me the remaining reports as soon as they have it, because it's also good, you know, sometimes we take notes, but maybe we may be missing a point or misinterpreting something, so it's always nice to have a second view. We will also reflect the work of the working group on the education curriculum. I already mentioned the notes taken by ourselves. And then input received from individual participants. So we have received a number of inputs already. And usually we should discuss everything here, because, you know, we want to be able to write that whatever this report is, it reflects basically the view of the participants in the symposium. So if you still, after we have discussed all the points here, feel that something essential is missing, please let us know right here, at least the basic idea, so that we can discuss with everyone, or that we can have everyone's approval to include this in the report, and the exact language and formulation we can still discuss. But, you know, if you come to us with a good idea after the symposium, we cannot really include it because, you know, we were not able to discuss it with everyone. If you have a small idea, small points, you know, still send it to us, that we can, if it's not a major recommendation or something, we can still include in the report. Yeah, so the most important part, of course, is the discussions in the present session. Now, when you look at the previous reports, you will notice that they follow a certain structure. And usually we try to keep that structure because, you know, people who read this report, they are familiar with the way they are structured, so they can read it very quickly. But I just wanted to explain to you the symposium structure so that when you read the report, you already know what's in there. So basically we have 4 main chapters, and the first main chapter is the introduction. And the introduction is more or less a formal part. It has 3 sub-chapters, A, B, C. And in subchapter 1, we just talk about the background and the objectives. You know, for all the UN activities, there's some kind of mandate, and we always have to refer to this mandate, because member states are always asking, why are you doing this? You know, is this the appropriate use of UN funds? So we have to tell them, well, you gave us the mandate to work on this, and this is why we do this report. And we will also reflect here the importance of capacity building in space technology development. Of course, you know, since it's our mandate, there must be a reason why we do this, because it's useful for mankind or for humankind, and we reflect this in this chapter. And then we give some background information about the program on space applications and the basic space technology initiative. In section B, we talk about attendance. You know, there's also another aspect about UN reports. We cannot put your names. So unfortunately, you know, we cannot say Mr. or Miss so-and-so made a presentation. That's just not by the rules. So usually what you will read is a very formal language, like the representative of country or the representative of organization. That's how we have to reflect you in this report. But in this subchapter B, we will say, you know, which countries or participants from which countries were here at the symposium, because the delegates at COPOS, you know, they're often very interested. Was someone from my country at this event? And, you know, what did they do? And at least then they can see, my country was somehow represented. And then in subchapter C, program, we talk about how the program was structured, you know, how we designed the program, that there was an international program committee, and that we had so many sessions and a poster session and panels. This will be reflected here. Then the second chapter, summary of the symposium program, will be a descriptive part. So we try to reflect all your presentations, but, you know, we usually have a page limit, so our reports are not allowed to be longer than 15 pages. This is also a cost-saving measure, and usually we meet the target. But that means also, you know, for each of your presentation, I have maybe 2 sentences or so. So I have to figure out how in 2 sentences I describe your contribution. And, you know, it's a challenge, but usually we can make it. So we'll describe the technical sessions here, and we will also reflect the panel discussions. And then chapter 3, that's the most important, because this is where people will be looking at. It's observations and recommendations, and we'll discuss this here in the next moment. And then we have some formal conclusions where say, you know, symposium was concluded, and what are the next steps, and where will we go next from here. Yeah, I should also mention, I mean, we'll be drafting this report, and I have a deadline, 12 December, so by 12 December, the report has to be finalized. The reason for this is we intend to submit the report to the forthcoming session of the Scientific and Technical Subcommittee, which is at the end of February. And the thing is that member states ask that all documents for a session are ready 10 weeks prior to the session, because they want to look at it and, you know, be able to discuss it or bring up questions. And it's of course a tough deadline because we have to translate this report. It also takes some time. So by 12 December, I have to submit this report in its final form to our translators. What I usually try to do is that I share the draft report with the chairpersons, for example, or with the organizers, so that they can still give some input if some last-minute corrections are necessary. Okay, but let's start with observations, recommendations. So what we have done is we've collected some information, and I just have put this on the slides, and I just want to show this to you, maybe read the text to you. And, you know, don't worry about the language. If a word is wrong, you know, if we don't use the correct technical terms, really don't worry about this. We take care of that, and we have professional editors who do this. But if an idea is missing, if we represent the wrong idea here, if we misstate some facts, please raise your hands. That's the most important for us to know. So usually in the observations, there's also some UN language. So, and the way it works is that we say participants at this symposium or at the UN Mexico Symposium, and then took note, observed, read, you know, there are some special words. And when you say took note, observed is of course an observation. And when we write recommend, it's a recommendation. So observation is an obvious fact, this is there. And the recommendation is something you say, you know, this should be done. And usually a recommendation should have an actionee, who should do it, and, you know, what should he do it, and by what time. So what I have here on the slides, you know, we may have to look also what is actually an observation and recommendation, but we'll also take care of that. So what we usually like to reflect in the symposium report is the observation of the importance of what we are doing, you know. And here's some wording. So participants at the UN Mexico Symposium took note of the importance of capacity building in space technology development, given the wide range of benefits that could be derived from such activities. And then, you know, we will give some reasons why there are these benefits. And we have heard in many of the presentations about the benefits of space technology development, and there will be more items here. You know, we'll go through the presentations and look if we find some more justifications for the benefits. But there, for example, opportunity to train engineers, the applicability, transferability to other industry sectors, opportunities for international collaboration, and benefits from actual application. So this is really to tell the decision makers this is an important thing to do. Participants then also took note of the speed with which developments were taking place in the field of small satellite activities, because we see this in the last few years. You know, when we started out in Graz in 2009, there were really only a few countries, few projects, and now we really have a proliferation of these activities. And we see this in a number of small satellites launched in the last 1 to 3 years. Our ITU representative had some figures here, 130 satellites alone in this year. We also see an increase in the capability of small satellite missions, I just mentioned that. And we see an increase in the number of operational small satellite missions. So actually, the capability and the operational use of small satellite missions is increasing, and that's a difference, I think, to the past when these were mostly training engineering missions. So I don't know if there are any comments on this slide. And if not, I take it that we can use this kind of language in the report. Please.
Question, how can we capture the idea that CubeSats and the basics of space technology is also useful for education of high school students, for example, the one that was presented from Israel?
Yeah, it's a good point. I think we'll capture this in the bullet points under the first big bullet here, you know. So certainly I think we've heard about this educating high school students, outreach, and so we'll certainly reflect this also here. Okay, so maybe let's go to the next page. You know, always this symposium was, and I've mentioned this also, it's a symposium that in a way focuses on the Latin American and Caribbean region. And we also want to reflect this, and we will work with our colleagues from Mexican Space Agency and CICESE to put some good wording here. But in general, you know, I think we can say that participants took note of the importance of regional and international cooperation, obviously, in the field of capacity building in space technology development worldwide. And maybe we can also reflect here the already ongoing many activities in the Latin American and Caribbean region. And then maybe we should also acknowledge the existing and proposed frameworks for space cooperation in the LAC region. And I mean, I just put here Space Conference of the Americas. Maybe we can have some reflection here. Then I forgot the exact formulation. There was the Central American Space Agency and an Association of Latin American Space Agencies. Yeah, so we'll put the correct terms here. And, you know, we also think it's probably a good opportunity to mention here Greg Tealc and point to the Regional Center for Space Science and Technology Education in Mexico. This, of course, is an existing framework for more closer cooperation. So we will certainly formulate this in more details, but I hope it's also okay with you, with the participants, that we reflect this in the report. Okay, so recommendations on long-term sustainability. So we are very lucky to have with us here a delegate from COPOS, so Dr. Agapov from the Russian COPOS delegation, and he provided us some input here concerning the discussions on the long-term sustainability of outer space. And I don't know if, Dr., shall I give you the floor maybe to explain a little bit the background of this recommendation here? Do we have a microphone?
Thank you, Werner. Yes, I will shortly explain. Right now, some of you know that right now we have ongoing talks on long-term sustainability of outer space activities, and because small satellites are becoming more and more say, important part of this activity from different points of view, both capacity building, education, outreach, and applications, practical applications, both commercial and non-commercial, then we have to point proper attention on the on how to properly build interaction between those people working in small satellite business or between community of small satellite people and between community of larger satellites, because not all recommendations which are applicable or suitable for larger satellites are applicable for small satellites and vice versa. So in this slide, I tried to point your attention and maybe attention of the copiers, because this report will be distributed among member state delegations at the STC and copiers as well. So this is an attempt to point the attention on importance of small satellites and importance of thinking on how properly to manage this new activity in space exploration in order to harmonize all those regulations or all those guidelines we're developing right now on the long-term sustainability.
Super. Yes, thank you very much.
If you have some specific questions, I will be happy to comment or to answer.
Mm-hmm. Thank you very much for this. I saw you.
Yes, as I mentioned yesterday, I understand the need for a set of recommendations for small satellites. However, and considering that probably 99% of all the space debris was produced by developed nations and spacefaring nations, of course, this is logic. And creating this additional burden on newcomers on the space arena may be very difficult to do. I think that what I will propose is that, yes, that those recommendations should be followed, but a period of grace should be given to new spacefaring, with nations with new space capabilities. And I won't say a grace period of 60 years like it was until now, but probably 10 or 20 years will be nice. And going a little bit forward with the proposition, I think that if the spacefaring nations, mainly United States, Russia, China, Japan, the European Union, and India, would like to do that and start right away, I think that would be a very good practice, but allow the rest of us this grace period so we can experiment and get to a level where we can incorporate those recommendations. I have more specific comments about how this will complicate small projects like the ones that we are doing. But, you know, I'll be happy just with mentioning just what I said. Thank you.
Thank you very much for your comment. First of all, I have to point out that long-term sustainability is not equal to just space debris issues. Space debris issue is just 1/10 or even less of this overall topic. And within the scope of long-term sustainability, we're trying to build the framework of which would be suitable and would be helpful to everyone, to large satellite operators, to small satellite operators. It's not just about space debris. And those regulations or rules or recommendations, guidelines we're trying to develop is a concentrated form of our knowledge we gathered during 60 years of space exploration. And we believe that these recommendations and guidelines will help you as a newcomers to pass this way or to find your way in very smooth and manner, not repeating those mistakes we made in the past. So the main intent of these regulations is not to harm your activity or not to kill your activity. So I see no reason why we have to differentiate large satellite operators or small satellite operators from this point of view, because we're trying to build something which would be helpful to everyone and which would help you to develop your small satellite business or small satellite activity in better fashion, I would say.
Maybe before Tom takes the floor, so thank you very much for this also. You know, it's a very interesting exchange, but we are getting on ice here. It's a little difficult. I should maybe explain one thing, you know. I mean, all these discussions about space debris and LT, long-term sustainability of outer space, take place in the Committee on the Peaceful Use of Outer Space, and these are discussions among member states, no? So your country is, in most cases, we have 76 members, is represented there, and actually this is the point where you have to bring up such kind of recommendations, you know. So and maybe this is something also we will reflect in this report, because what we try to do is we want to bring you, the small satellite community, in contact with your representatives who are sitting in the committee and who are having the deliberations, the discussions on all these issues, and also take the decisions. You know, it's not so helpful to put this in this it's a way, would be a way in the report, but it's a little bit a complicated issue. So the more important issue would actually be for you to talk to your representatives in the committee and assure that these views are properly reflected. No? But it's a very interesting point, so it's, I thank for this. Maybe let's quickly take Tom, and then let's have a look at what is actually written here and if this is agreeable.
Okay, I just want to quickly add something, because it seems there is a conflict not only between the traditional space-faring nations and the new space-faring nations, as we have seen here, but also between the universities that want to experiment and the traditional guys with the big satellites. So one thing that came up to my mind was during all the discussions would be there are some people that want just to experiment, as you has pointed out, just need a very low orbit lifetime actually. And then there are the others which want to use it for big scientific grade or commercial grade missions. So why not try to propose a kind of a new deal in space, where basically the big guys say, okay, for us it's very important that the space has a long-term sustainability. So we will support the guys that do experiments by lowering their launch cost, but under the condition that they go to a very low orbit. So basically, there could be a fund which which could be done by the big players which have a long-term idea, and they get because most of the existing nations have the means to put satellites up there. So by deliberately putting up the experimental satellites in a really low orbit, supporting the new guys and actually giving them a benefit, so they can do it for lower cost, and the other guys have the advantage that the orbits are not filled up by these experiments. So that might be something to contemplate about.
Okay, so it's a very interesting idea, and I think that causes a lot of discussion here. I don't know if we should take that, but keep it very short, yeah, because we want to go back to the.
I'm sorry, but if this report is going to reflect what was discussed here, as it says, noted that, I don't think the last point was noted.
Well, you note it now.
It is a suggestion to be included, or was something that was really discussed and noted?
It's a suggestion based on the overall discussions we had. You know, we discussed space debris, we discussed the frequency things, and of course this is the time now to modify this.
But not specifically this point.
So let's take this point by point maybe.
Increase the detectability of the satellites in order to keep them tracking all the time by radars and facilities. Not something that was discussed here, or even simpler as place at the orbit in the satellite. Maybe even more complicated, it was not discussed.
Okay, I suggest we take this now point for point and see what can be agreed, what needs to be modified. So the point here was participants noted the ongoing discussions on long-term sustainability of outer space activities. I think we had discussion about this, and I just encourage all of you to have a look at the COPOS discussions under LTSSA, and which one is working group 4 or the one dealing with small satellites?
Yeah.
So expert group D.
It's expert group D is a regulatory, expert group B is operations and space debris.
And I should mention, we had these discussions, for example, last year in Dubai. We had actually the chairman of the working group on long-term sustainability here, so he wasn't able to join us this year. But so this is something that the small satellite community should be familiar with. So, but I hope we can reflect that there's agreement, that we can say that you noted, or at least we tell you now, that there are discussions ongoing on long-term sustainability of outer space activities in COPOS. So this is the first bullet. Now let's go to the second bullet. Noted that such discussions should include various aspects related to exploration of outer space with small satellites. So this is a proposal by Dr. Agapov. He's actually part of these discussions. And I think it's a nice point, you know, to say that somehow the small satellite activities should also be considered in these discussions. Can we agree on that, or? So we have this point. Okay, then let's go to the next point. Development of recommendations to operators of small satellites, especially of constellations and swarms consisting of dozens or even hundreds of objects with short operational lifetime regarding the optimal orbit regimes that could be used in full consistency with existing and developing practices devoted to space debris mitigation and safe on-orbit operations. So I understand this is a recommendation to the expert group or to the working group.
Yeah, to the working group, yes.
So it basically, I think we had this discussion earlier here already that I think Professor Marbo was mentioning that space agencies, for example, are asking for a legal framework to know, what are the rules in which we should kind of operate, because that helps, for example, commercial businesses to know, what they are allowed to plan and do to actually be in compliance with existing frameworks. James?
Sorry, I mean, you need to take out the word small.
Mm-hmm.
I mean, implying that only small satellites are the problem is a slur on the small satellite community. And how do you differentiate between something like Iridium, which is a commercial constellation, with Rapid Eye, which is a commercial constellation, with Planet Labs? I mean, all satellites, if there are large numbers of them, should be taking into account these aspects. But the word small satellites, rather than just satellites, is implying that somehow the small satellite community is less responsible than the rest of the community. I think that's an insult to the small satellite community.
Here, unfortunately, the recommendation is not reflected right now. The idea was, behind all this observation or recommendation, is to specifically mention satellites with short lifetime. Because normally those satellites you mentioned do not have short lifetimes. And usually...
Sorry, you're still pigeonholing a specific type of satellite into a... You're making assumptions about it. I mean, there are lots of big missions that are turned off by space agencies after 3 or 4 years because they don't have the budget. There are lots of small satellites which have been shown to last 12, 15, 20 years. You can't differentiate by using the word small satellite. Just put satellites, and you can't disagree with that, because it's true that every satellite operator, if they're putting large numbers of satellites into orbit, should be taking these aspects responsibly. It's not just small sat people, anybody. Iridium, Galileo, GLONASS, anybody putting large numbers of satellites into orbit should be taking into account sustainability, not just the small sat community.
Okay, I will try to explain. Right now, everything you are talking about larger satellites, which are operating, or even smaller satellites operating for a long time, already covered by those regulations or recommendations or proposed guidelines already developed. But by some reason, the smallest satellites like nanosats, picosats, femtosats are excluded of this discussion. And the idea behind of this recommendation is to point out attention of COPIOS and its subcommittees and the working group on LTS that this satellite community of tiny satellite exists. It is not presented just by 1 or 2 or 3 satellites. It's a large and growing community, and their needs and interests have to be taken into account properly. This is the idea, because right now, yes, I agree. We can write the general statement here, and I fully agree with you that this statement have to be applicable to any satellite. But here, I especially pointed out small satellites, because they are, by some reason, I don't know why, they are excluded of the discussion. So.
Yeah, I think maybe we should point out, I think there was a discussion in COPOS, as you said, about small satellites, and in fact, it wasn't excluded, or?
Yeah, I can give you an example. At the last COPIOS session in June, we raised the question on small satellites and how this small satellite activity fits those recommendations and vice versa. And what we have in response, that it's too early to discuss this topic on small satellites because it's not significant. But we believe it's significant, it's important, and that is why we think we have to mention this.
See, Attila?
Sorry, there is still a missing of understanding. I tried to address this yesterday in my presentation, and this is exactly the same missing of understanding also on the COPUS. Please understand that the whole UN system, also COPUS, also ITU, is service-oriented. That's why on the COPUS there are, during the LTS sessions, there are a one-day session, let's say, related to the geostationary orbit, after then meteorological satellites, after then RNSS, navigation satellite, but as a small satellite doesn't exist as a service. Exists now a small satellite group, but I was listening here today also, a lot of you had applications to early warning, disaster monitoring, meteorological tracking, whatsoever. That's why my very friendly recommendation is that the best solution for the CubeSat operators will be as soon as possible to join the particular services which exist for 50 years from starting of the satellite service. But, on the other hand, to help, I understand that it's not so easy. For this reason, COPUS and the LTS instructed Outer Space Office and ITU to prepare handouts, because also the LTS is a little bit shaky to say, we don't know how to touch the small CubeSats. That's why we try with Werner and his team and my team in ITU to prepare handouts. We will see the reaction of the LTS. Last year on the legal subcommittee there was one-day workshop on the small satellites. That's why, and presentations. After then Professor Marbo organized on the Vienna University one-day workshop. That's why we are trying to put a torch in the night to the CubeSats, but this is from both sides. You have to pick up also this task, because if you stay silent, if you will not come to the legal technical subcommittee, CubeSat community does not exist. It's a university teams, some research institutes, but please don't think that we will solve for you the problem. This is exactly as I told you yesterday. If you are not coming to the Working Party 7B meetings to say what are the technical needs and requirements for the CubeSats, forget that somebody will solve for you this, and the WRC 18 will close the door in 1 minute to say there is in fact no issue on the CubeSats. CubeSats go to the services as allocated, that's all. That's why this is just for explanation why there is a discussion, and even COPUS is not able to touch correctly the small CubeSat community up to now.
Thank you very much for this. I mean, let's just have a look at this third paragraph. I mean, what does it actually tell? It says, you know, that small satellite activities to be used in full consistency with existing and developing practices developed for space debris mitigation and safe on-orbit operations. I mean, I think that's obvious. You know, whatever is in place, you should follow that, you know, international law and so on. I think that's not even up for discussion. No? But basically what it says here is it's a recommendation to operators, so basically give you more guidelines on how you can be in compliance with what is already anyway existing. So this doesn't really give you new limitations or anything. It just would give the small satellite community some guidance on how to be in compliance with what is already there. That's how I understand it. So maybe, you know, we can still reformulate this and we have one.
So the way that I read it is really targeted to the optimal orbital regimes that those small satellites should be recommended to be in. So it is relatively limiting. So it is not just how the small satellites will be compliant with the existing and developing practices, but it's really targeted to the optimal orbital regimes. So I just wanted to highlight this. So.
I'm going to be very quick here, but one of the things mentioned yesterday in the briefing was the finite lack of people actually registering their launches within the UN guidelines and getting the registration. This is something uniquely important to small craft. I used to work in space surveillance for the Air Force. Really small CubeSats are incredibly difficult to track with radar and some of the other ground-based sensors and things. So it's very important that there's that registration regime. So I think putting that piece as far as the debris mitigation, if you will, I don't really like to use that word when talking about registering, but if you're not registered, then you might as well be a piece of debris for somebody else to worry about. So I think that is something that's important, but I also think that's something that's unique to very small spacecraft.
Mm-hmm. So I think this is actually, thank you very much for this, this is actually captured in this last paragraph, development of recommendations to designers of, and it's called the smallest satellites, and we look at that, how we reflect this, which would call to consider design modifications that will increase the detectability of the satellites in order to keep them, to allow them to be tracked all the time. So something like that. So again, we will change the wording and make sure it's technically correct or something. But that would be that one. I mean, I see we don't have full agreement yet on bullet point 3. Maybe let's skip bullet point 3 for the time being now, and let's come back to that later and see how we can do that.
I think overall, looking at the whole thing, the issue is the small satellite. What is small satellite?
That's actually the good point. Yes. There's no definition.
And then the two second last bullets is already kind of assuming that the small satellite community has to abide by the existing constraints, by the existing rules.
Absolutely correct, because a small satellite is a satellite like any other satellite.
So, but based on the discussions that I'm hearing here, I think perhaps if we can consider another option of treating the small satellite community perhaps as an experimental group. For example, like in aviation, they have licensing for the experimental aircraft, which is treated quite differently than commercial airlines. Mm. So maybe that's one approach for us to give this special consideration for small satellite communities.
Yeah, thank you for your question, but I don't agree with you, and that's why. In general, there is no difference why some disaster in space happened, because improper design of large spacecraft, or because the small satellite having some exclusion collided to other orbital object. So that is why we're trying to develop common guidelines applicable to all satellites. And if you combine the recommendation in bullets 3 and 4, you will see that these recommendations are devoted to improve tracking situation with small satellites and limit their orbital lifetime, because they are very hard to track. You can put your small satellite, which costs $10,000, or another $10,000 into space. but in order to provide safety of operations of other spacecraft, which this particular small satellite may collide, you have to invest hundreds of billions of dollars in order to build appropriate space surveillance systems. It's, so we're trying to find the balance between all of this. We don't tell you, don't launch these satellites, but we're trying to find the better way on how to fulfill your interests and interests of all other community operating satellites on orbit. That's the goal, nothing else. Not to kill projects, not to stop this activity, but to find the way of living together in space. And this way have to be safe.
Thank you very much. I think this was a good statement. We'll also include this somehow in the report, this balancing the interests, and that is our goal. So I suggest let's keep the third para out here, and let's maybe quickly go to the next point, and then, or one short, very short. Yeah?
Short one. I just would like to point out that the collision of the two, I think Iridium and one of the dead satellite, Cosmos, that generated more small satellites than the number of satellites launched. And furthermore, there are actually other boosters. I know of several rockets that just went up, deploy certain things, and they're excluded from this list. So I think, to be fair, that satellite should actually be changed to a man-made space objects.
Okay. Short replique.
I don't see the reason to applaud, because we not exclude anything. Right now, we're seriously thinking about how to make space more safe, because space itself is a dangerous environment. Yeah, it's not safe environment by its nature, and we made it even more dangerous because we were not thinking in the past about some consequences. And right now, we are thinking on how to revert this situation, not to make it worse. That is why we are trying to develop some guidelines which will help us on this way. That is why we recommend for all new activity that all new activity have to be performed in such a fashion that which would not produce more danger.
New activity also means new launches. There are launches in the past 3-4 years, and I know of a few that's coming up in the next few years that will generate debris. I know that. I had direct discussion with NORAD. I know that they can track small stuff with their S-band systems and things like that. We were talking about how to name an object that was to be released by a rocket because of some other issues. And that object actually becomes a dummy. That one launch created at least 2 debris, one at 800 and the other one at 600 kilometers.
Okay, so before I give the word to Professor Mabo, just there's a very interesting discussion. We could probably add on 1 or 2 days to this symposium to have it in, maybe at the vineyard today you can discuss it.
I just wanted to make a short remark because I come from Austria, a very small country, and we are not, let's say, a big spacefaring country. We have only last year launched our first 2 CubeSats and small satellites, and it was really a big adventure for the small country of Austria. And but I can tell you that we are now very proud of the fact that Austria is by the ITU and by others taken as a model example how you should do small satellites. So we did not consider talking with Attila Matas or other people from space agencies who were concerned, in particular French people are very concerned about more space debris. We listened to them carefully and tried to do, I'm talking we, I mean the Austrians who built that, and really did our best to conform to these rules, and still be able to launch a CubeSat, a university a satellite like made by students and so on. So we achieved our goal of launching the first small nano satellites at the same time complying with the rules. So I think that's our particular pride now, 1.5 years after the launch, that it was possible and that we are taking in the UN, Professor Kutelka from Austria was invited to speak on the podium and as an example of how this could be done and should be done, a small satellite project. So I would encourage the newcomers and other, let's say, emerging space nations not to see it as an obstacle or impediment of developing space projects, but rather feeling encouraged and supported by the big players, because they are very helpful in this, and then still be able to do our own projects. So don't be so, let's say, defensive, I would say. Thank you.
I think that, very quick, last one.
I'll try to be brief. We do see some of the recommendations as a possible impediment, and let me go back to the subject of space debris. We don't have many opportunities as secondary payloads. We have to take whatever is available. If there is a rocket that goes 740 kilometers, like happened to us in Argentina, and is willing to take our satellite for little money, we need to take it. So if our satellite is going to be there for 30 more years, we have no option. So I'm just stating that in some cases, these recommendations may hamper our ability to put our payloads in space.
Okay, we leave it by that, and we'll discuss this this evening. And maybe at some stage we'll make a special symposium just about this topic, 4 days, and we'll look at this. Okay, let's look at the next recommendation here. And again, this is a very interesting recommendation: development of recommendations to national authorities on proper management of projects involving the use of small satellites. I don't even want to discuss this in more detail because it's actually happening. So last year, the Committee on the Peaceful Use of Outer Space requested the Office for Outer Space Affairs to develop a handout for small satellite actors on what they have to do. And I have this later in my recommendations. We'll somehow combine the text here on this slide with that other text. So this is basically already a fact. We don't even have to recommend this anymore. This is maybe, oh God. A recommendation that acting in a spirit of cooperation and transparency and considering the goals of provision of safety of on-orbit operations as the key point for the future exploration of the outer space for the peaceful purposes, designers and operators of small satellites should consider. So this is just, not a recommendation, it's basically observation or that what should be done. And, actually we have had this in past reports. So, and I think it's sensible, it's an observation, again, in the interest to keep space available for us, for activities in the future, that there are certain best practices, and I think there are some best practices mentioned here. So, satellite design modifications in order to increase the radar cross-section, by the deployment of depot structures and so on. So this was mentioned about the detectability, about the tracking of the satellite. I think that makes sense. Satellite design modifications should increase the effective error to mass ratio of the satellite, shortening the orbital lifetime. We have discussed this in many previous symposiums, so deorbit mechanisms, and it's obvious, if you want to be compliant with the IDC guidelines, for example, 25-year rule, you may have to have this. These things are being developed. They, being tested right now. Implementation of onboard GNSS techniques in order to provide more accurate near real-time orbital data. I think it's also sensible. Options for launch of small satellites with short operation lifetimes into orbits where natural perturbations help to shorten the orbital lifetime. This is exactly what Pablo just mentioned. When we don't have enough launch opportunities that go into low orbit, we have the space station right now, but it would be nice to have dedicated launches that go to a low orbit. And you may have other recommendations on what can be done. We certainly have also collected other things, but I hope it would be acceptable to have this. Octavia?
I'm sorry, but Again, none of these recommendations were discussed here except the last one. So they are all very nice recommendations, but they were not discussed here. So I don't think it should be included in a report of the symposium.
So when you read it now, could you accept it, or you would consider it unacceptable as it's...
Unacceptable, because they were not discussed here. So except the last one. So if the report is going to reflect what was discussed here.
No, but I mentioned that the report is also based on the discussion right here in this session. So whatever is being brought up, and we have asked individuals to provide us with input, and we discuss it here. So it's brought to your attention right now. But of course, you can disagree with this, but not on the basis that you say, it's...
It should be said, and it is a recommendation of one participant.
So you disagree, and do we have other views? Should we delete these points here? What is the general view? Huh? So what's the overall feeling? Is there a feeling that it's not appropriate to reflect this? Or? Okay, so if that's the feeling, of course we follow the... So is it agreeable to leave the last point, and will we somehow reflect this in the report? Okay, that's one.
Hi. Maybe we could add, instead of techniques to, deorbiting small satellites. This was mentioned. I can't remember the name of the last presenter. Maybe provide more hardware or modification for deorbiting small satellites, which could also provide solutions.
This would be the first bullet, or something alongside the first bullet?
It's not exactly. This is mainly to maintain...
Oh, it's the second bullet, no?
Second bullet?
Sorry, when I edit, you can't see it on the screen, so something is wrong with the computer, but I try.
I'm not talking about tracking, but deorbiting small satellites.
Trying to get the screen back here, just a moment. Yes, just some technical problem. Okay, so this was the item about, small satellite modifications to shortening the orbital lifetime. So we have discussed this, you said, so we could include this. Okay, we can formulate it. It doesn't have to be, it's not necessarily that it's mentioned word by word, but the idea has to be there, no? Please?
Yeah, and I would recall you that yesterday I mentioned specifically on problems about tracking. So this opinion was expressed. So why we have to remove it?
Yeah, but that's okay, It may be one presentation. That's why we try to have consensus now, If you say this is a wrong idea or it's technically wrong or so, then we remove it, no? But so
because from my point of view, I can tell you that all these topics were discussing at the expert group B of the working group on the LTSSA, and we raised all these topics, and we include them into our report by expert group B, and you can download this report from the USA website. And these recommendations are devoted to help you not to kill you. So why to remove this? My idea was that this report could be another option to remind to the committee and subcommittees about the importance of this issue. Not a personal, it's if you take the expert group B report, it's not personal, it's as STSC of member states representing here. And yesterday at least 3 points of this, maybe just one was not mentioned on GNSS techniques.
It seems that many people here don't agree with you. I don't agree, the other one here, maybe we could vote United Nations. I don't think we should put a GNSS every satellite.
But Octavia, you know, again, the issue is here, I think this is a useful advice. Not? I mean, the question is, but by removing, I mean, what do we win, or what is the advantage? You know, if it makes sense to remove it, let's remove it. But if it's useful advice, it's something, you know, these are possible ways.
My concern is that it will be seen as this was approved by the symposium. This is my concern. If it is not the case, okay, but I think if the report is going to reflect what was discussed here and agreed, so it will seem that we all agree that increase the area or increase the reflectance or whatever?
Again, it's a consideration, you know. It's not that you should do this. You should say these are ways on how you can be compliant, you know, with what rules you have. And you should consider this, take this into account. And it's one option for you to do that. No? It's not you have to do this. You have on each satellite, you have to have deployable structures, and that is not what we are saying. No?
The organizers.
So I'm just wondering, is there another view that it's inappropriate to reflect these ideas, or is this... Okay, let's leave it also like this, and maybe, Octavio, we can get together afterwards also and discuss this so to see what we do here. I have another, you know, yesterday we had a very interesting discussion about balloons also, presentation, and we saw that balloons actually can be used to test space equipment. And so we talked to the presenter of this presentation, and he said, you know, why, you know, when we have all this debris situation and you just want to test your hardware, you don't necessarily need to go into orbit, possibly. You know, you can just put your payload on a balloon or also on a suborbital rocket for testing. And I think he provided this input here, and I think that could actually fit with the recommendations that we had earlier. It is also a means to contribute to space debris mitigation. So again, the wording we will change, but an alternative to actually testing something in space, maybe a short suborbital flight or small stratospheric balloons. I think it's an interesting idea to reflect that. So I hope you will agree that we also include this as you know, a possible idea. Okay.
I'm just wondering if anyone here is familiar with, there was a conference on orbital debris in Washington, D.C., I think it was about 3-4 years ago. Are you familiar? Do you know about this? No? Okay. I have not seen any subsequent conference of that, unfortunately. But however, in that conference, there are actually two fronts being presented. One is obviously this, that, you know, small satellites are orbital debris and whatnot. The other front actually presented the fact that if you remove just I think 2 or 3 dead satellites, then the orbital debris issue will stabilize. Hence my point of the 2000 debris that was generated by collision of 2 large satellites. 2000 debris are actually more than the sum of all of the small satellite launched. And I have not seen that kind of a recommendation coming out of this discussion.
I mean, it's a good point, and again, we could discuss this probably for hours, but also I remind you, yesterday we had a very interesting chart, I think also in the ITU presentation, about the number of, you don't call it occultations now, how do you call it? Conjugations, no? And he showed, for example, the number of conjugations by CubeSats compared to NVSat. Of course, there are more than one NVSat-sized payload there, but it clearly showed that the conjugations caused by the CubeSats are way higher, several times that of one large satellite. No? So, and I remember, we mentioned the Austrian satellite. I know the Austrians, the Bright satellite, every few weeks they are scared that their satellite will not survive because they have a conjugation. So, I think it's a problem that we cannot deny. No? And of course, you can try to trade it off, but in the end, we are all affected, and the big players have to fulfill the same rules, they have to be subject to the same scrutiny. But I think you are, the small satellites community, you are in a weak position. You are not the big guys with the big money. And I think you should be a community that's exemplary. You should actually say, we are the ones, the good guys, We adhere, we do it right. We develop the technology for deorbit. It's us who do this, who test this, and who will contribute to keep the space environment clean. And then everyone will look up to you and will say, yes, we have to do it like you do it. No? So I think we want to get you to that point. And hopefully these recommendations or items will bring us there. So if it's okay, we'll also include this somewhere as a suggestion, as an idea, just to reflect it, and then we can always say the small sat community already knew it a long time ago how to do it. Yeah, James?
I just want to make sure we're not confusing 2 points. I think everybody's happy with recommendations which are specific to the smallness of a satellite. So something about tracking, something about deployables, increasing surface area, that's specific. Whereas when you put a word like small satellite next to the word intolerable, you're implying that there's something inherent about smaller size satellites that is causing the problem when there is a problem caused by satellites, caused by launch vehicles. So I think we should stick to recommendations specifically using the word small or pico or nano, which do reflect their size. What I'm getting is, the only thing I can compare it with is racism or sexism. It's implying that the small sat community is somehow different or somehow less responsible than the rest of the satellite community. And I think that's not a fair reflection of this audience, certainly. Maybe it is in other colloquia, but if you're trying to report this symposium, then I don't think you really would get that general view from this audience. And I also back up Dr. Durao saying, unless it's been discussed, you can say we're discussing it here, but it's not as if there's been 3 or 4 papers on a specific subject like using GNSS for small sats for traceability or space traffic management or anything. We haven't had those discussions. You can't say that 10 minutes talking between 2 people here is a recommendation of this symposium. Likewise, you can't say because it's been discussed at another symposium, it should automatically be applied as a recommendation to this one. I think that's just a point of order.
That's a good point. I guess with regards to the small satellites, we'll reflect it somewhere in the report that, of course, everything here is for all satellites. But of course, since we're talking about a small satellite symposium, we're in particular looking at, we've been discussing small satellites, but I absolutely agree, we have to make it clear, we are not singling out small satellites and that they are subject to certain rules, the other satellites are not. No? And with regards to your point of order, I suggest really we get together maybe and discuss these open items then together so that we can resolve these problems here. I just want to go through the other recommendations here because we want to conclude, of course, and go to the vineyard. So recommendations on legal aspects, we always have in the report also, noting the necessity to adhere to existing obligatory legal frameworks relevant for space activities, both in national and international law, and I had this in my presentation. So, this is, we want to bring that to your attention. There are these legal frameworks and, you should be in compliance with that. Attila?
We are repeating always that we are dealing with unexperienced users. Probably it will be good to add the international law ITU radio regulations, for example. I don't want to say not the international outer space treaties, but when we say international law, I will be happy to see their ITU radio regulation. It's up to others what they wish to add.
Mm-hmm.
It's true. I mean, both national and international law, ITU radio regulations are international law. I mean, either you put an, for example, or you mention such as the UN space treaties and ITU regulations, but ITU regulations are international law.
Okay. So I've made that note, and there was a recommendation. I think one presenter said that the recommendation that every space project should consider to include legal management in addition to technical and administrative management. So I thought that's maybe a good idea to notice also. Good. Now we come to some recommendations made by our ITU representative. So participants at the UN Mexico Symposium noted that member states and small satellite operators are urged to follow the ITU radio regulations related to the use of frequency bands and notifications of small satellite systems. I think that was clearly made in the presentation on Thursday afternoon, so I hope this is acceptable. Recalled that member states and academia are invited, and I think the invitation was made, to actively participate in ITU P7B studies related to small satellites. On question, what was this, ITU R2547, characteristics and spectrum requirements of satellite systems using nano and pico satellites in order to participate in the exchange of views and decision-making process with the ITU to be finalized at the World Radio Conference 18 in 2018. I think Attila wants to.
Just as W is missing, that's why ITU R and up to then WP, Working Party 7B. WP 7B.
So I think this...
now to remove the 1P more and the space.
Just lost my cursor. Just a moment, there's a technical problem always with the... So I think this is very important, that the small sat community is aware about these studies, and that actually we had this kind of recommendation already for 2 years in our symposium, and I still understand that the small satellite community is only sparsely participating in the work of this working party. So again, don't be, as Attila said, don't be surprised if there will be rules and regulations that will make your life harder in the future, activities.
I think that it could be also very important to perhaps to notice or to stress that the use of radio amateur bands are not for any commercial use. Because we are talking, or I don't know if it's necessary, but in the near future there are going to be perhaps operators based on small satellites, and I don't know if it's okay or not, but it's important to notice.
So I put this in here, and then the exact formulation we can look at. But yeah, we had these discussions, I think, also in the past already. So it's maybe good to reflect this also. Okay, there's a second page on ITU-R. So participants noted that member states are invited to actively participate also at the World Radio Conference 15 related to various satellite service general items, and we'll put the URL in here so that you have more information. And then noted, and this is resolution 757 of World Radio Conference 2012, regulatory aspects for nano and pico satellites. And that this resolution invites WRC 2018 to consider whether modifications to the regulatory procedures for notifying satellite networks are needed to facilitate the deployment and operation of nano and pico satellites and to take the appropriate actions. And I think it's also necessary for the small satellite community to see what is happening there and, you know, to act accordingly in your interest. And then finally, a note that there will be a special conference in Prague held from 2nd to 4th March 2015. And member states, academia and satellite operators are invited to actively participate at this ITU Small Satellite Regulatory Symposium and Workshop. I think it's also to make this important link to this event here. Good. Yeah, I just wanted to mention, I think I did show this in my presentation, and that's linked to one of the other observations before. Actually, the 53rd session of the legal subcommittee of COPUOS requested the Secretariat, and the Secretariat is the Office for Outer Space Affairs, to develop in consultation with ITU an information handout on issues relevant to registration, authorization, debris mitigation, and frequency management with respect to small and very small satellites. That's the wording used by COPUOS, for the benefit of space actors intending to operate small and very small satellites. This has already been decided and is an ongoing process, and you know, we want to make sure that you are aware about this, and we'll present probably the first draft very likely at the Scientific and Technical Subcommittee in February 2015. So keep looking at the OSA website for the draft handout. So a recommendation, and there I need your support. Participants endorsed the continuation of the activities under the work program of the Basic Space Technology Initiative. So as I mentioned, this symposium is being held under the BSTI. And I mean, we have the mandate of COPUOS to do this, but I also need the mandate of the community. So if you think it's not good that we continue these activities, then you have to tell me now. Otherwise, I hope we can continue, and I have your support, the office has your support. Thank you very much for this. And yeah, what's very nice, and we'll hear in a moment about this, so we heard today that South Africa has officially confirmed that South Africa will host the UN, not Mexico, but the UN South Africa Symposium on Basic Space Technology in 2015. We'll have a small presentation about this in a moment. So I hope we can reflect this, and just thank South Africa for this invitation. Yeah, there will be just reflections of the education curriculum. So we would be happy if you would note the continuing work, there's a spelling error here, on the education curriculum. And then there was also a recommendation that the education curriculum on space engineering, or whatever the name will be, should include lectures on various aspects of development, launch, operation, including debris mitigation and practical use of small satellites, so the aspects of long-term sustainability of outer space. So I hope, you know, I guess it's appropriate that new engineers are being taught about these aspects. That this is important. This is something you need to consider in your mission design, and you know, if you could just reflect this in the report as a recommendation, that would also be very nice. Okay, Chisato, you have some. Yes.
I just wanted to confirm about the word launch. Does it mean launch opportunities?
No, I guess it's more or less, you know, like in what orbits you can launch, what launcher you can use, and what options you have, and what this means with regards to long-term sustainability, for example. So the choice of launcher.
Choices of launcher, because
yeah,
in the working group it has been discussed the curriculum will exclude the launching vehicles.
Yeah, no, you're not asked to provide lectures about how to design a launcher, no? But
I just wanted to make sure.
It's about a satellite. You need to know what options you have in terms of launchers. Yeah, that's the meaning. Understand? Okay, and then there is another general recommendation. You know, we always have the problem, we need to close the link with COPOS. So COPOS gives us the mandate to organize these activities. We make the symposiums, we write a report, but often what happens, if there's no one to promote the report gets lost. And so actually there's a recommendation to request the Office for Outer Space Affairs, or the Secretariat, to bring to the attention of COPOS the increasing role of small satellite activities in the peaceful use and exploration of outer space through a technical presentation on the observations and recommendations and on the outcome of the present symposium to the Scientific and Technical Subcommittee at its session in 2015. So if you would endorse this recommendation, you would basically give the mandate to the office that we make a presentation on, you know, on the symposium here, on what we have achieved over those 4 days, and of course also on the observations and recommendations, and that would close kind of the connection back to the committee. And of course, if we have this, we would also work closely with the host country, with Mexico, and you know, we could probably share this task, or eventually maybe also Mexico could make such a presentation, so we could discuss this in more detail. So if we have your endorsement that we can make a presentation on this activity here, and we would of course also stress the role of the small satellite community and the importance of these activities, and things would be a good outreach activity. Good, this in principle concludes the observations and recommendations we have, so I think we'll still get together maybe on these points with regards to the long-term sustainability. Maybe we need some discussions here, and then we can consult also with the host country about how we'll reflect this in the report. But basically that concludes these discussions. If you still have any small points, you know, I mean, some issues or so, still please bring it to our attention. So you can just email me, or you approach one of my colleagues, Chisato or Sonia, and you know, anything that can help us to improve this report will be very good. As a next point, I just wanted to remind you, you know, symposium feedback. So you saw you have this feedback form, and also we already kindly asked you to complete this feedback form and hand it in at the registration desk. If you haven't done this, please do this. This is extremely helpful to us. You know, if you feel organizational aspects where we could improve, what was nice, what was maybe not so nice, what would be more helpful in the future. And then also in terms of the symposium, you know, are there topics we should cover? Did we forget any topics? Should we set aside more time for discussions? That's what we are always being told, but then we don't have time for presentations and other things. Should we make the symposiums longer, shorter? So any suggestions you have are very welcome. So please complete and return those feedback forms. That helps us very much. So as I already mentioned, we'll be working on the symposium report. We will be consulting with chairpersons, with the host country, with some other people who have made observations, recommendations to make sure it is a good report. And it should be available in February 2014, hopefully before. So I may be able to post the draft version on the website a little bit earlier. 2015, thank you. Oh God, time is passing. And symposium report presentations, I understand you will get a memory stick, or there will be memory sticks available to take home the presentations, but as soon as possible we'll also post them on the symposium website. So if you don't receive a memory stick or lose it or whatever, in at least within the next 2 weeks you can download this from the OSA website. Please also check this other URL for future OSA events. So we have a number of other conferences planned next year already. Space weather, small satellites, human space technology, wildlife management using satellites, using space assets. So there's a number of interesting topics. And you know, you can apply. We do have some funds, especially for experts from developing countries. We collected your email addresses, of course. We usually do not share this. It's not in the participants list. We don't post it on the website. If you need to contact another person, you need some information, you can always contact the office and we can try to relay email addresses to put you in contact with other people. Of course, use the opportunity here to exchange cards. But with your agreement, we will also include your email address on our mailing list. It's a very low-level mailing list, so we have maybe 2 or 3 emails per year. It's not that much, so I hope we don't spam you. But if you don't like this, please also tell it to me or my colleagues so that we can exclude you from this mailing list. We are still looking for host countries for 2017 and beyond. So if you like this symposium and if you think your country would be interested in hosting such an event, please let us know. It's not quite that easy because the UN, you know, if you are a university or institution, we cannot deal directly with you right from the beginning. We need to have an agreement with your government that can take up to a year or longer. So the earlier we start, the better. And of course, there are some funding requirements or co-funding requirements for the host country because UN has a limited budget. We try to use our budget to bring in experts by providing air tickets, and of course anything the host country can provide, as it was so excellently done here in Mexico, is helpful to make a nice symposium with many participants. Yeah, and finally, and I invite now James to come up here. We heard today that South Africa will be hosting the symposium in 2015, and we'll now have a short presentation about what's going to expect us in South Africa next year.
Thanks. Hopefully a very short presentation. I'm nothing to do with the organising committee. We'll probably end up just being a sponsor. I only heard last night that officially we've sent the right pieces of paper to the UN to agree our government support for hosting next year. I say it will be in Cape Town almost certainly because that's the heart of where the space, well, everybody's space, academic and industry is in the Western Cape, near Cape Town. So obvious, where are we in South Africa? We're in the south of Africa. Western Cape is one of the provinces of South Africa. Most people think that Cape Town, the Cape is here. Actually, the Cape is this little sticking out finger here. And when people first went round the Cape, they thought that they'd got round the bottom of Africa, and they hadn't. And this little bay here is called False Bay as a consequence, because they got round this bit and thought that was it. So Cape Town is a big area here. We're near Stellenbosch and Somerset West, which is the wine region of South Africa. Cape Town, beautiful place, most famous for Table Mountain, you can see in the background. Cape Town was basically built in the mountains and is a beautiful place to be. In terms of climate, we haven't got a date for the conference yet. It'll be probably October, November, so similar time to now, which means it'll be springtime because we're southern hemisphere. So at the moment we're in springtime, just going into summertime. So it can be pretty warm, all the way up maybe even to 30, 35 degrees. But we're right on the coast, and so bring a raincoat because when it does rain, it rains very, very hard. It's like tropical rain, but not warm. Not very nice. And the other thing to point out is everybody, the first thing they do is they try and go up Table Mountain. Table Mountain is 2,000 meters high, and you see people up there in t-shirts and shorts freezing to death because it's very chilly up there, especially if the wind's blowing. Transport-wise, it's very easy to get to. There are international flights direct to Cape Town, which is 20 minutes away from, the airport's 20 minutes away from the centre of town. You can fly direct from most of the European main hubs. From Dubai is a big centre to get into to Africa from. Singapore, if you're from further afield, there are flights from almost everywhere to Johannesburg, and then it's a further 2-hour flight from Johannesburg down to Cape Town. And I think it's something like, it's certainly one of the 10 busiest routes between Johannesburg and Cape Town. So there are flights every hour between the two. So there's no long layovers in Johannesburg if you have to go that way. A lot of people have a very strange perception of Africa, including I did. I mean, you think of it being jungle and people running around with bones through their noses and spears. Cape Town is just like Europe. It's very European. It has dual carriageways. It has internet that works, power that doesn't go off, drinking water straight out of the tap, that kind of stuff. It's a very civilized place. So the road structure is excellent, but and you can just jump on a bus from the airport into town. I would warn anybody who looks at the train service that they think they might get a train from Johannesburg to Cape Town. The train service just does not work. So avoid it like the plague. The other thing, people have a very bad reputation or very bad opinion of South Africa in terms of security. There are, as in any major conurbation, some issues in terms of petty theft. There's certainly, it's a very poor country. There's a lot of poverty, and you will probably meet beggars on the street. But in my experience, no worse than somewhere like San Francisco or Portland on the west coast of the States. You just have to be careful of things, but the reports you hear are not nearly as bad as you hear in the press. Johannesburg is worse. Cape Town is a very civilized place. You can go out at night on the streets, no problem. The university base, we're in the Western Cape because of three main universities, CPUT and their French collaboration of SARTI. They've launched ZARCube 1, which is still working, very successful. They're working on ZARCube 2, so lots of CubeSat experience there. University of Stellenbosch, Professor Herman Stein's very famous in his field for doing attitude control systems, and they're one of the key parts of the QB50 platforms that are being proposed. I think already 15 of those are being used on QB50. And it will probably be hosted at University of Cape Town. University of Cape Town don't build hardware, but they do masters and PhD courses in space, usually things like space law and some of the sort of softer aspects of the space program, rather than building electronics and mechanics. Industry-wise, there are two main groups. There's the SES Space Group, of which New Space that I run is part of. So this is small industry, the small medium enterprises. Space Tech is the large government-owned space company that's doing the current national program, ESAT-1. They also own the big facilities. There's a very good environmental test facility out in the mountains, about an hour and a half away from Cape Town, called Howtech. ISIS have a very small office in South Africa. I know a lot of people working with ISIS. Samira and Delta V are two other small companies doing space mechanical design and camera design. So most people don't know that South Africa is doing lots of stuff in space, but we do and have been since the 80s. So just summarize, great location, very easy to get to, although it is a 12-hour flight from Europe. All over land, it's just straight down south. Very good climate, very good food, fantastic. Apologies to the vegetarians here, but there's some great steaks, and they do like to chop up their wildlife and serve that on barbecues. A lot of fish there. The wine is absolutely outstanding in the region, and it's where the space community for South Africa is based. So a very warm welcome from South Africa. Hoping it will come next year. If you can't wait that long, and you've got some spare air miles, Monday week there is the second African CubeSat conference. As I say, starting on the 3rd of November. So if you haven't got your tickets yet, go buy them now. Thank you very much.
So thank you very much for this presentation. So we are very much looking forward to next year in South Africa, and the application will probably open around March, April 2015. So please look out at the OSA website. So basically this concludes session number 9. So I thank you all. It was really a great time. I think we'll have very nice observations, recommendations. It was a great symposium. I hope you use this opportunity to meet more friends, new friends, and it will be beneficial for your activities. And now I ask Mr. Enrique Pacheco from the Mexican Space Agency to be the master of ceremony for the closing session.
Thank you so much, Werner. Well, this is the farewell words that we want to express. I'm going to say some practical announcements just before to leave. Thank you. And this kind of events is not possible without the work and the intense participation and enthusiasm several people. Just to give some numbers, in order for all of you to be comfortable and have all the necessary to do this very fruitful discussion and interchange of opinions, on this occasion you were supported in some way or another for more than 30 people that make possible that we have everything in place to have these discussions. And as acknowledged to all of them, always when you personalize the recognize of the people, probably somebody get left out of the list, but we are going to try our best in order to mention all these aspects. Initially, to our sponsors, you see the logos of all the sponsors, the federal government by the Ministry of Communications and Transport, of course. As a Mexican space agency, we are part of the Ministry of Communications and Transport. United Nations by the Office of Outer Space Affairs. CICESE as a host institution has been a wonderful work, having these fantastic views and on all the facilities to enjoy it and make this really a very, very excellent place to have the discussions. The local university, the Universidad Autónoma de Baja California, that is the local university with the Ensenada campus, and the state government, the government of Baja California, that make easy for us to have yesterday, for example, the cultural event in the cultural center is part of the states. The Ministry, Secretaría de Turismo del Estado, that is the Tourism Secretary of the states that provide funding also to have part of the events. The Municipal Council that provide us all the facility to have the Riviera in which we enjoyed all the cultural event. And CONACYT, of course, CONACYT also provide a very important funding for this event. And CONACYT is the head of all these public centers like CICESE and provide a lot of opportunities, not just for doing the event possible, but also is going to a key enable for the future activities of space activities in order to continue to provide grants and provide funding to make possible all the projects that we start to discuss in these aspects. To our private sector sponsors like Honeywell, we want to express our gratitude again to UK Trade and Investment that is the sponsor for the dinner tonight. You are really going to enjoy the dinner tonight, and it was possible thank you to the support of UK Trade and Investment. Also Axon Cable and Interconnect that support the event yesterday. And so all the sponsors are really play a key and important role in make possible all these aspects. Particularly in terms of the local team, to CICESE, I want to give ask to all of you to give a round of applause to Jorge Preciado, that was the head of the Jorge make a wonderful, a very, I think that we put and add some white hairs to the heads because it was really intense work during all these weeks. And the local team from CICESE, let me mention, and at the end I am going to ask to offer them some round of applause to Alesia, Janit Resendiz, Walter Julián Arce, Carlos Víctor Aragón, Rosario Fuentes, Roberto Conte, Saúl Rodríguez, Luis Enrique Lenes, Carlos Espinosa, Juan Hernández Arroyo, Verónica Rojas, Cristian Méndez, Julio César Escobedo, Cecilia Irata, Enrique Lenes, Saxia Irene y en general todo el equipo local del CICESE que fue apoyado por colegas estudiantes de la UABC. I don't make I make the mention of the names and I follow the discussion in Spanish, sorry for that. All this local team was supported also by students from the local university and that was Jorge Luis Sánchez, Hernando Murillo, Gabriel Rosas, and Gerardo Alegría. All of them are part of the local team that make possible that you have everything in place, that help was the faces that you look to solve all the drivers from CICESE that take you from the airports and are going to take you back safely. They are fantastic and always try to wait for you until the last minute just to arrive safely to here. So I'm going to ask to all the local team a round of applause for the excellent job that they do, please. Also, we want to express our gratitude to the United Nations Office Affairs Office that also was head-to-head working with us and giving all the support, particularly to Sonia Bejarovic, Chisato Kobayashi, and of course Werner Balog, that is the mastermind, and all the enthusiasm, all the support, all the activities are possible, I think, on this series of workshops. In many, many aspects, thanks to the enthusiasm of Werner and the vision to continue to provide these opportunities to make a fruitful discussion in several regions, several countries, and we are really, really thankful to all the United Nations Affairs Office for all the intense work. Thank you so much. And on later is going to come and of course Dr. Mendieta, that is our head of the Mexican Space Agency. Without his support, this will not be possible. I want to give a special thanks for all the confidence for him to make. And to all the team of the General Director, that is Julieta Pacheco, Talia, and Belinda Flores was a core team that provide us a lot of support. Julieta is over there. The other two are still in Mexico City. And personally, I want to express a really, really great gratitude to all my team, because without my team, this could not be possible. This kind of events always produce a lot of pressure for them. You look me so happy and so relaxing thanks to this wonderful team that I have that make me feel very comfortable all the time. Sometimes they have a really, really hard time, and I want to express really my gratitude to my directors, Rafael, that is here, Rafael Torres, and the two other directors that are not here, but they support a lot of work from here. That was Benito Orozco and Marcela Torres, and the local team that was supporting here was Virginia. You all really familiar with all these names. Virginia Janesian, Itzel Pineda, that is on the back, Sandra Cabrera, and the two others, members of the team, Anaí and Fabiola, that are in Mexico City. But these faces that you saw, thank you so much, all of you, and please stand up just to welcome all of you. Thank you. So I really hope that nobody was left out of the list. Sometimes this is the big challenge. We have some practical announcement before give the word to Dr. Mendieta to make the official closing of the event. We are going to leave the buses from the hotel. Now from here to the hotel, you are going to have time to make all your, lift your belongings and remove the tie and be ready. And from the hotel, we expected to leave. You
might be 5 there in Valle.
10 before 5 is going to leave the first bus. At 5 is going to leave the last bus. The idea is to arrive on time to the vineyard in order to have a proper. At the end, now that you left the room, please be sure to take the memory stick and the ITU CD that was not possible to deliver yesterday to all of you. And as far as I understand, Jorge have a particular announcement related to one thing more that we need to.
I'm a small one, so I need a step. Okay, good afternoon. Our team from CICESE and Mexican Space Agency want to thank you for coming to Mexico, to coming to Ensenada, and to coming here to CICESE. We hope that you felt like in your home. I don't know how your home, but we hope that you felt like in your home. Everything that begins must end. But before this, we have a gift for you. It's a pleasure for us, the local organizer committee, to provide you with this special souvenir that has been made by a group of artisans named Cuatro Etnias. Every piece of this has the name that what artisan made it. What's the paso el video, no puedo. Dale. Okay. Cuatro etnias mean four ethnicities. The cultural wealth and tradition of Baja California have been preserved by natives of the Qumai, Cucapá, Pai Pai, and Quiligua tribes. This product you will have in your hand represents one of the highest expressions of ancient civilization in the region. After you visit to Ensenada in Baja for this symposium, it's a wish that you have something with you such this special gifts that has been elaborated with the same care and technique that it was made by the artisan and center. Take a piece of the Ensenada with you. So our team, we have to give you one, and inside has what it was made, and the name of the artisan was in this place. Okay? Yeah. Thank you, and I hope to see you in Cape Town. If they take me with you.
They are going to take all the souvenirs on the back and provide all the souvenirs on the together with all the things. Okay. So let me now give the floor to General Director of the Mexican Space Agency, Dr. Francisco Javier Mendieta, just to make the official closing of the workshop. And thank you all of you. Thank you.
Okay, I'll start talking. It's quite late. We have to leave in a little while. Firstly, I am very glad to be visiting South Africa next year, a country and a city with which we share good food and good wine, of course, good high technology. For CICESE, for the Mexican Space Agency, this has been very fruitful. All the discussions, all your opinions, your will, and your enthusiasm. And it has been as well for the Ensenada municipality, for the Baja California state, and for Mexico. In general, I think this will be a very good milestone for our Mexican space program. Finally, we have to collaborate. That's the key word. If we can have a keyword and only one keyword for this symposium is collaboration, cooperation, interaction, networking. The global challenges that our countries emerging spacefaring are enormous. Global change, climate, disasters, digital divide, security. And collaboration is the only way. And this symposium has been a lot of insight, input, gravitating around the small satellites, but it can be scaled up not only to device, but the service, the network, the vision to provide the knowledge of our people and the technology of our scientists, engineers, legal people, administrators to the service of these human needs. On the other side, all has to be materialized in local, in regional changes. I mentioned this region where you will have an interesting photograph. As those who were last night at the Husong's Cantina, it's considered as only entertainment place, but it's always for basic science. This is a team observing an eclipse, a sun eclipse several decades ago, and that means that in Ensenada, in Baja California, there is not only cold beer to go, but also good science, good technology, and good networking. As, for example, the space has provided this region with many benefits. We have observed our ocean from the space for our ecology, our fisheries, our coastal phenomena. We have observed our land for our earth sciences activities, for all the faults, geological faults that are threatening our region. The space has provided us connectivity. This is one of the best connected states in Mexico. And also we have been tackling many border issues because the border is complex, the border is challenging, and with collaboration with our neighbor country, with our brother country, we have used the space for the benefits of the border. For example, to tackle the security problem, the transport, the trade, the immigration, and the ecology in the border. And that's why we have this as a mega region, a binational mega region. And finally, after watching this photograph, the space has allowed us also to observe our wineries for agricultural, water, diseases, and production. But any space observation needs in situ validation. Then now I will propose to make an in situ validation of our wineries to have good wine and good food. Thank you very much.
Está llegando el del Sam's Club.